All right, welcome back, everybody. We're going to move into lesson number 3, or module number 3, I should say, of our Implementing Cisco Secure Core Technologies course. Implementing and operating, I should say, Cisco Security Core Technologies course. In this module, describing common network application attacks, we're going to talk about really just kind of basic network type of attacks. Things like password attacks, DNS-based attacks, DNS tunneling. We'll talk about web-based attacks, HTTP 302 cushioning, command injection attacks, SQL injections, cross-site scripting and request forgery, and then finally we'll wrap up this whole module by talking about email-based attacks, and we'll do our summary challenge. So as we go through this discussion here, this is another one of those self-study sections that we go through. We're going to talk about how do we implement password attacks, what are the different methods, what is the difference between a brute force attack as opposed to a dictionary attack, what is a phishing attack, and so on. Password attacks themselves are a way or provide a mechanism for harvesting credentials so that we can log into a shared resource like a server or some other protected resource within our enterprise that we wish to gain access to for other nefarious purposes. If it's stealing information, if it's gaining access to a system so that we can pivot from that system to attack another system in the network. When an attacker is able to gain access to specific resources, they end up having essentially the same rights as anybody that would be authorized to that particular system would have, and as such they would have the appropriate privileges to compromise the system, to create backdoors for future access, or to change privileges or escalate privileges to gain further access into other systems within the enterprise. So we have to understand what is the importance of protecting passwords in our environment, what is a password hash, what would be the point of creating a password hash, and so on. We should also be aware of the different types of attacks against standard web-based applications that we have in our enterprise. Things like DNS or HTTP, email services, and so on. How do we identify these types of attacks, like a DNS-based attack, a DNS tunneling attack, a web-based attack, or command injections, or HTTP 302 cushioning attacks, and so on. We also need to know that DNS is often used by attackers to tunnel malware to allow us to install and communicate to a command and control server in a botnet. So when we're looking at packet captures with DNS traffic, if we're doing some sort of an incident investigation or we're trying to correlate some events that may have happened on the network, we need to be able to examine those DNS queries to see if those DNS queries are being used to tunnel or carry suspicious traffic in the network. Web-based attacks, obviously very, very common, being that most web applications are trying to access resources online, like for web pages and websites and web information. As such, this is a good place for us to implement different types of attacks based on poor website coding or zero-day vulnerabilities that might exist that nobody has been presently made aware of. So we'll look at things like databases and how databases become a frequent place for attacks in the network, the structured query language or SQL, using this particular application to query a relational database, and what is a SQL injection attack, why are the databases attack targets, how can we reduce the attack surface by protecting those particular assets in our enterprise. So we're going to take a look at how these web-based attacks, how DNS attacks, how email attacks work, how command injection attack techniques work, SQL injection, and so on. Now, probably one of the most common types of attacks that exist today, and certainly one of the easiest forms of attacks that exist today, is what we call a password-based attack, right? Passwords obviously are used to gain access to many different systems, especially legacy systems or common databases or common systems that people might access as an internet-based resource and so on. But password-based attacks are very, very common. Passwords provide access to, particularly with kind of less secure systems, single form factor authentication to databases, to resources, to accounts, banking accounts, or whatever it might be online, social media accounts and so on. And obviously passwords need to be secure. However, the password standard for a lot of community sites and a lot of community resources is not nearly as strict or as stringent as what we might see within our corporate enterprise. Now, as a security analyst and as an information assurance individual, you need to be aware of what types of password attacks exist. And we're going to talk about a few of these in this section here. We'll start by talking about password guessing, which is probably the least common form of a password type of attack. We'll talk about brute force attacks, dictionary attacks, phishing attacks, and so on. Let's start by talking about password guessing. Password guessing would be using some sort of tool to automate the process, or using some sort of manual process to potentially guess a password based on information that you may have collected from that individual. Maybe it's their birth date, the names of their children, or you might even just simply try what some of the most common passwords that might exist on a particular system. But password guessing is typically a lone attacker who's making some sort of informed guess as to what a particular password might be. It could be simply that you click the hint button. On Windows, you can go and click the hint button, and it might give you a hint on what that password might be. And that hint might give you enough information so that you can at least make an educated guess as to what that password might be. Now, the next one that's listed here is the brute force attack. Brute force password attacks consist of an attacker basically going through a whole bunch of iterations of either passwords or passphrases with the hope of eventually guessing the combination correctly. We systematically check all the possible passwords and passphrases until we find the correct one. Now, we could alternatively go through a process of attempting to guess the key, which is created from the password using some sort of key derivation process as well. And this is what we would refer to as an exhaustive key search. But a brute force attack is basically a process in which we are guessing very quickly, checking maybe short passwords, maybe longer passwords. We'll talk about a dictionary-based attack a little bit later on. But by definition, brute force attacks are typically, we're not using pre-computed hashes like we would in a rainbow table. We're not using a dictionary of passwords. We're just simply kind of using random constructs of what a password might be. All right. Basically, what we're doing is we're trying to calculate every possible combination that can make up a password, and we're testing that to see if it's actually the correct password. As the password length increases, the work factor, or the computational power required on average to find that particular password, is going to increase exponentially. There is a concept called the password haystack that we talk about. How secure is your particular password? Well, a lot of people would say, well, the password haystack is going to be effective by having simply a random password with lots of random characters, lots of random choices that's a specific length. But the reality is that the complexity of the password has far less of a security effect, a positive security effect on the password itself, than the password length. So passphrases tend to be something that we would consider to be much more secure than some sort of completely random password. The idea of using a random password that's very complex and difficult to remember is somewhat counterintuitive, because if it's difficult for an attacker to guess the password based on randomness and length and complexity, then it's also difficult for the user to remember the password. So oftentimes other ways of remembering that password will end up essentially negating the amount of security that we've implemented from having the password in the first place. Somebody might write down the password, somebody might store it in a notepad document on their computer, or they might simply do a cut and paste or store that password in an insecure manner. All right. The resources, like I said, to do a brute force attack are going to grow exponentially with the increasing variable size or the key size, not linearly. So in the past, we typically worked with very small key spaces if we're talking about a key, or very short passwords if we're talking about a password. But in essence, the concept of a brute force attack is a way for us to essentially kind of go through all the different iterations of passwords. Think, for example, if you had a ATM card and you only had a 2-digit PIN code. That means you would have 100 different iterations of possible combinations of a PIN, right? Because you would only have really 100 different numbers to go through, 00 through 99. And if you didn't implement some sort of other security mechanism, like collecting the card if there's too many failed attempts and not returning the card, a lot of the ATMs and devices nowadays don't require you to actually insert your card. They just want you to swipe it or dip it. But, we could have some mechanism like that, or if we take that analogy and extend it over to the password world, password lockouts or at least delays between failed login attempts, it would be relatively easy to go through all of the possible iterations of that particular password. So when it comes to brute force attacks, the countermeasures that we put into place, the tools that we put into place have more to do with changing the overall concept of authentication. Instead of relying solely on password-based authentication, we will do some sort of multi-factor authentication. We'll have strict password policies, password history retention counts, password account lockouts, account disablements, that kind of thing for failed login attempts. There are many, many different types of tools that are available to us to do brute force password guessing. AirCrackNG, Cain Enable, Crack, Dave Grohl, Hydra, John the Ripper, LoftCrack, OffCrack, Rainbow Crack, and so on. And there's more than just those. Now, on the flip side, a dictionary-based attack. A dictionary attack is technically a form of a brute force attack for defeating some sort of authentication mechanism or password-based authentication mechanism by determining what the key is by trying millions, at least millions, most likely more than thousands, but millions of likely possibilities, such as words in a dictionary, previously used passwords, or variations of words in a dictionary. In essence, a dictionary attack is based on trying all of the strings in a pre-arranged listing that are generally derived from words found in the dictionary, which is why we call it a dictionary attack. But there are huge lists that are available that you can download that actually contain hundreds of millions of passwords, not only passwords of common dictionary of common passwords that may be used, but also a dictionary of passwords that have been discovered in the past from previous breaches. There's cracking software that can use these lists and produce also common variations, such as substituting numbers for similar looking letters, and so on. The dictionary attack tries only those possibilities which are likely to succeed. So we're not actually going through just simply random combinations of what a password might be. And dictionary attacks are usually pretty successful because people have a tendency to choose shorter passwords that are either ordinary words or common words or variants of those particular combinations. And we simply append a digit or punctuation, or we do some sort of character replacement and so on. Because, the reality is that most commonly used password creation techniques are covered by these available lists, and combined with cracking software pattern generation, it makes it very, very easy to crack these passwords. A safer approach is to either randomly generate some sort of very complex long password, 16 characters or more, but again, that's a little bit counterintuitive, because that means that not only does the attacker need to remember that or discover that password, the person that's actually utilizing the password, the authorized person, would have to somehow remember that. A passphrase or using some sort of password manager-based application would be probably a little bit better, okay? The idea is we're trying to achieve a time-space trade-off, reducing the work factor by basically pre-computing a list of these potential passwords. It's very much how a rainbow table works as well. A rainbow table is a pre-computed list of hashes. We can't really necessarily decrypt a hash, but we can recreate it or regenerate it. If I have to go through the process manually and calculate manually all of the different variations of encryption or of a hash to see if the hash output matches the hash that I'm aware of, that would take a lot of time. But if I could go through and do this in advance, pre-compute a list of hashes, and store that information, and then simply reference that with pointers, it would be much, much easier. So basically, a rainbow table attack is a pre-computed dictionary attack that has a whole bunch of pre-computed hashes for commonly used passwords and so on. All right, we only have to generate that pre-computed dictionary one time. Once it's completed, the password hashes can be looked up almost instantly, comparatively speaking anyway, at any time to find whatever the corresponding password is. That's why we circumvent, or wouldn't say circumvent, but we negate the usefulness of these pre-computed dictionaries by storing passwords with a salted value. The salt itself is not hidden. The salt itself is not a secret. But if the salt was used to create the hash, but the dictionary was not created with the salt, guess what? That makes the dictionary completely useless. So even though the attacker may know what the salt value is, they would have to take that salt value, they would have to recalculate and recompute using that salt value the hundreds of millions of entries within the dictionary. And by that time, the salt is most likely changed, because salts are generally temporal. Even though they're not hidden, they're generally temporal, almost to the point of a new salt is used every single time you generate a hash for a particular password. All right. So basically what we're trying to do is we're trying to make pre-computation infeasible. All right. Again, dictionary type attack software can enable Aircrack NG, John the Ripper, Loftcrack, Metasploit, Aircrack NG, I think I already said that one, and Offcrack, I should say, are ways of, or applications that we can use for these dictionary type attacks. Now, a phishing attack is a social engineering attack that allows us to try and capture sensitive information or data, like somebody's credentials, usernames, and passwords, possibly credit card information, and so on, by disguising ourselves as a trustworthy entity in some sort of email communication. It could be through instant messaging, it could be through text messaging as well, but text messaging we typically refer to as smishing. Instant messaging could be considered phishing as well, but typically the term we use to describe this process when it comes to electronic mail exchange is phishing, P-H-I-S-H-I-N-G. All right, and the idea is that we're going to create and craft an email that looks legitimate, looks like it comes from a legitimate site. It has the appropriate logos. It has the appropriate verbiage in the email. It could be even look something like something as innocuous as a payment receipt through PayPal, or an email from eBay suggesting that eBay's new security policy requires you to authenticate and verify some questions. But we try to give it the look and feel of a legitimate site. This is an example of a social engineering attack which is specifically designed to deceive users. Users get lured into communicating to this trusted site through social media, through email, through auction sites, banks, whatever, because the email looks completely legitimate. The challenge with this type of attack is that it is difficult to block. Certainly we can use advanced applications like Cisco's email security appliance or other email protection mechanisms, but quite frankly, the biggest level of the biggest way that we can remediate these types of this, or kind of limit the attack surface for this type of attack, is through training, through disseminating information to our end users to say, this is what you need to look for. You need to look for these types of these signatures, if you will, within the email itself. All right. If you suspect that you have an email that is, potentially harmful or a phishing type of attack, then what you'd want to do is you'd want to maybe, send it to the security team, the IT security team, and have them analyze it, or contact the vendor, eBay or PayPal or Citibank or whoever it might be, or just simply don't click on any links in the email. Log into eBay directly or log into Citibank directly to see if, in fact, the email is positive information. There are different variations of phishing types of attacks. There's a spear phishing attack. These are basically phishing attacks that are directed at specific individuals or a specific company. We're not doing bulk phishing. We're geared towards getting information about a specific target in a spear phishing attack. There's a whaling attack as well. Whaling attack would be a spear phishing attack directed specifically at individuals that have a lot of influence within an organization, senior executives or some other high-profile target. The Fancy Bear threat group 4127 used a spear phishing tactic to target email accounts that were linked to Hillary Clinton's 2016 presidential campaign. They attacked over 1,800 Google accounts and implemented the accounts-google.com domain to threaten those particular users. And they were relatively successful with that. All right. Catfishing, or, is a spelled with a PH in this case, is deception that involves getting to know someone closely to gain access to information or resources. They're the mark, I guess you could say, to get control over that particular target. There is another catfishing concept, right? Catfishing spelled with an F, very similar, but in terms of cybersecurity is a distinctly different concept. We're creating a social network presence as a sock puppet or as a fictional person in order to finagle someone into a romantic relationship or whatnot. We've seen all the TV shows about that on MTV and so on. Clone phishing, another variant of this type of phishing attack where a legitimate and previously delivered email containing an attachment or a link has the content and the recipient addresses taken, and then we use that information to create an almost identical or cloned email. The attachment or link within this email gets replaced with a malicious version, and then that is sent from an email address that's spoofed to appear to come from the original sender of the email that was cloned, right? Now, typically this type of attack requires either the sender or the recipient to have previously hacked for that malicious third party to get access to that legitimate email that it would be coming from. All right. Oftentimes accounting firms, auditing firms, they're going to be phishing targets as well. Voice phishing, or what we refer to as vishing. The concept of voice phishing is a message, a voice message that claims to be from a bank that tells a user to dial a specific phone number regarding issues with their bank account. Once that phone number is dialed, it's going to prompt the user to enter account numbers or a PIN or something to that effect. Vishing, voice phishing, uses things like fake caller ID to make it appear as though the call comes from the United States or at least comes from a trusted organization or something like that. Smishing, SMS phishing, uses cell phone text messages to deliver the bait to induce people to provide their information. So maybe it's click this link or call this number, contact this email provided in the message or whatever it might be. And then we'll kind of encourage the victim to provide their private data, credentials or whatever it might be. And then based on that, we were able to capture that information. All right. The techniques, typically some of the most common techniques are link manipulation. So instead of citibank.com, it's www.citibank.example.com, right? So it has a subdomain of Citibank, which some people would say, well, that looks legitimate. At least the layman anyway would say that looks legitimate, but in fact it's not legitimate, right? Also, when you hover over a link, some people might look at that and they hover over a link and they see the tags. The tags are modified. The displayed text for a link, basically what is displayed between the A tags, if you will, suggests a reliable destination, but when you actually click on the link, it takes you to a different site. All right, there's website forgery type of phishing. There's covert redirection, of course, social engineering techniques, and so on. We can also do offline attacks. Offline password attacks, as the name suggests, would be we get a copy of a password database, hashed passwords, whatever it might be, and then we can go through offline iterations of trying to recover those passwords. Online attacks are a little bit more difficult because in an online attack, the activity is visible to the system, and the system can lock an account after too many bad guesses. Plus, online attacks just simply take too long to produce. And the lockout period makes the work factor exceedingly difficult. Remember, in terms of cryptanalysis, work factor is how much time does it actually take for me to go through the process of achieving my goal. And if the work factor is simply too large, if it's going to require too much time, and then on top of that, we add into this whole concept the idea of temporal passwords, that becomes a really problematic situation for the attacker. All right. Also, a lot of systems are going to have minimum password lengths. They're going to enforce a specific character set, meaning uppercase, lowercase, numeric, special characters, and so on. They're going to retain password history, so you can only use passwords if you haven't used them for the last year or whatever. But, you know, the tide is changing, right, when it comes to passwords. The traditional password complexity requirements that we've identified usually are not going to be used anymore in enterprises. We're either going to do MFA, some sort of multi-factor based authentication. We're going to rely on other authentication methods like digital certificates on a common access card, or biometrics, or even multiple factors of authentication. Or we're going to use passphrases, which tend to be a little bit more secure. All right. So two-factor or multi-factor authentication means that you have to do something, you have to say something, you have to provide something that you have to provide something that you are, and so on. And each of those factors are considered in authenticating. An ATM is a perfect example. You can't just simply go up to the ATM and put in a PIN code and get access to the information. The PIN code is something that you know, but you also have to provide a credit card, or debit card, I should say, or ATM card. The ATM card has a chip on it. That chip has a secure ID and security mechanisms built in. And then based on that, something you have, plus entering something you know, you've done multi-factor authentication. All right. Which password attack type is characterized by trying every possible character combination until all the combinations have been exhausted? That would be a brute force attack. If I'm just randomly going through a whole bunch of different iterations, I'll start with 2-character passwords and go to 3-character passwords and so on. But we're talking about not dictionary words or variation of dictionary words. That is a brute force attack. It's not to say that you can't have a brute force attack with a structure. You could say, okay, this is my character set that I'm going to use in this brute force attack. Alphanumeric characters, symbols, etc. And let's just start to go through different iterations of this character set. All right, let's get into our next topic here, DNS-based attacks. Now, before we get into the specific types of attacks and these very large and imposing numbers that we see on the screen here, it's important that we have a general understanding of the purpose of DNS. I think a lot of you that are watching this video have a pretty good idea, but I want to kind of fill in some of these things before we get into the actual specific types of attacks that could exist within this within this protocol, right? DNS as a protocol is a hierarchical dynamic database that provides mappings between host names and IP addresses, both for IPv4 and IPv6. It also contains text records, mail exchange information, what we call MX records, name server information, what we call NS records, and security key information, which are defined as resource records. the information that's actually contained within the resource record is grouped into different zones, which are maintained locally on a DNS server so that that information can be retrieved globally through the distributed DNS architecture. As a protocol, DNS operates both over TCP and UDP. TCP typically for server-based transactions, UDP for client-based transactions, and specifically port 53. All right, now if UDP is used as the transport, retransmissions and sequencing is not going to be a function of UDP, but DNS does have those components built into the application. So DNS as a whole is composed of a hierarchical domain name space that contains a tree-like data structure of linked domain names, which we would refer to as nodes within the tree. The domain name space uses these resource records that could exist to store information about the domain. Not everything is going to be stored, but certainly a lot of information is stored. This tree-like data structure for this DNS space starts at the root zone, which we simply identify as a dot. That is the top level of the DNS hierarchy. It usually doesn't, it's not something that we would typically see within the application, but we would see the information that is trailing that particular dot as defined as the fully qualified domain name. For example, Cisco.com would represent the root zone. From that root zone, the hierarchy gets split into what we call subdomains or branches or subdomain zones. Each domain name has a label. The labels are separated with a dot. And we can have up to 63 characters within that label. The fully qualified domain name, what we would refer to as the FQDN, contains up to 255 characters, including those dots as well. And these labels essentially get constructed from the right to the left. The label at the far right is essentially the top level domain for that domain name. And then as we move to the left, we move to the more specific elements of the tree itself. So com, for example, would be the top level domain for www.cisco.com because that's the label that's the furthest to the right. All right. So if we are looking at the domain name system hierarchy at dot being at the top, everything below is considered a kind of a substructure of that. It could be a .com, .net, .org, .gov, .us, whatever it might be. All right, and then below that, we would have the domain of maybe Cisco.com. And that domain space is the Cisco.com domain. All right, then below that, we might have tools.cisco.com or www.cisco.com, whatever it might be. All right, that's how the general structure works. DNS was actually specified as an implementation that was originally defined in RC 882 and 883, but some additional RFCs, I think 1034 and 1035 have kind of updated those. In order for us to understand the potential vulnerabilities of the DNS protocol, we're going to talk about several of those vulnerabilities in this particular section here, is we need to understand the terms that allow us to describe the general functions of DNS. A resolver, for example. This would be just any DNS client that sends a DNS message to get information about a particular domain name space. The recursion is it's basically what we do when the DNS server is actually asked to query on behalf of a resolver, meaning that resolver sends the request to the DNS server. The DNS server needs to maybe forward that request or recurse that request on behalf of the resolver itself. An authoritative server is any server that actually responds to the query messages with the information that's actually stored in the resource records for that particular domain namespace on the server itself. All right. A recursive resolver would be any DNS server that has to recursively query for the information that was originally requested in the original DNS query. The fully qualified domain name, or the FQDN, is the absolute name of the device within the DNS database. The resource record itself, we won't get into the details or the specifics. We'll talk about some of the components, namely TTL. That's one of the DNS Cache Poisoning attacks involve manipulating that TTL field. But the resource record is basically just a format of the DNS message. It has a name field, it has a type field, it has a class field, a time to live field, an RD length field, other fields as well. I think there's an RData field as well. And then the zone, we've mentioned zone a couple of times already, is essentially the database that contains information about the domain name space that's actually stored on the authoritative server that we would eventually browse to and resolve from. All right, so the idea of DNS as a protocol is simply to translate human readable names into an IP address, or we could actually go the other way and translate IP addresses into human readable names. This translation process is actually done on the DNS Resolver. It could be a client application, it could be a web browser, or it could be a bind application. It doesn't really matter what it is, but we send the DNS query to the DNS server requesting the information that we're trying to get. And then based on that information, we get information that was defined in the resource record. All right. Now, what we see on the screen here is something that was comprised in the 2016 annual security report, which identified that over 91% of malware used DNS to facilitate its attack, or at least as a function of its infecting a computer or whatever it might be. That's a very, very significant number. More alarming, though, is that 68% of organizations, and these were based on IT security professionals that were questioned or queried by Cisco, state that 68%, or at least 68% of those professionals, said that the organizations don't actively monitor how they manage DNS within their organization, or even the DNS messages that are being sent back and forth within the organization. And that's pretty significant if you put those two numbers together. All right. Now we're going to talk about specific types of attacks that exist within DNS. I think that's important to understand. What is a Dns Open Resolver? What is Dns Cash Poisoning, Dns Amplification and Reflection, resource utilization attacks, and so on. And we'll talk about those in this particular section here. All legitimate DNS messages are sent and received in multiple sections. These sections of the DNS message contain the fields that will end up determining how the message is going to be processed by the device that receives that particular information. These individual sections also contain information about the query itself. The device asking for the answers, the device, basically saying, hey, I want to get this information, and other components, right? The header, the DNS message includes the header, the question itself, the answer, the authority, and then finally additional information. All right. There are things or flaws in the implementation of the DNS protocol that really allow it to be exploited and used for nefarious purposes, for malicious activities. Because DNS plays such a critical role in internet functions. Pretty much every operating system, every application, makes use of this particular protocol, but it also means that you absolutely have to harden your DNS servers so that they are not used maliciously. All right? And that's really what this whole topic is. So the first thing that we're going to talk about is what is a Dns Open Resolver, right? And it defines it here. A Dns Open Resolver is a DNS server that allows DNS clients that are not part of a particular administrative domain to use that server to perform recursive name resolution. Basically, open DNS, right? These are servers that are going to give answers to queries for anybody on the internet. 8.8.8.8, Google's DNS is considered an open resolver. Cisco Umbrella has a couple, 208.67.222.222 and 208.67.220.220. Umbrella being more of a hardened product, though, and more specific to what Cisco is doing, offers some level of DNS security to block known malicious sites, to block sites that are known to contain malware or botnets or phishing websites and so on. We see that open resolvers have three major vulnerabilities, including Dns Cash Poisoning, Dns Amplification and Reflection Attacks, and Dns Resource Utilization Attacks. Let's start by talking about the actual Dns Cash Poisoning Attack. Basically, a DNS Cache Poisoning Attack is the act of entering false information into a DNS cache so that the DNS queries will provide incorrect response information and user information, and then those users are going to end up being directed to the wrong websites. This could be also referred to as DNS spoofing, the IP addresses of the internet, which would, spoofing those addresses would enable web traffic to arrive or at least be directed to the wrong location. Dns Resolver Caches are basically the directory. And when those particular caches store faulty information, traffic is going to end up going to the wrong place until that cached information is corrected. Note, this doesn't really actually disconnect the real websites from their IP addresses. We're just poisoning that particular information. Because there's typically no way for a DNS resolver to verify the data that's contained within their cache, incorrect DNS information will remain in that cache until the actual time to live value expires, or until an administrator or technician or whatever removes that information manually. All right, so there are many, many different vulnerabilities that make DNS poisoning possible, but the biggest problem is that DNS was built for a much smaller internet based on the principle of trust. A more secure DNS protocol, and we'll talk about this a little bit later on in this section here, called DNSSEC, is hopefully going to be able to at least fix a lot of those particular problems. Right? We already talked about generally what a DNS resolver does, right? A DNS resolver provides clients with IP address information that's tied to a particular domain name. We take those human-readable website addresses like Cisco.com and we translate them into machine-readable IP addresses. So when I attempt to navigate to a particular website, we send that request for Cisco.com to a DNS resolver. That DNS resolver then responds with that IP address, and the browser takes that address and loads the website and does whatever it needs to do to transact that information. All right. Now, DNS resolvers will actually save the responses of IP address queries for a particular amount of time. We can, so that means that basically in the future, I can respond to those queries much more quickly without actually having to go to a whole bunch of servers in this DNS resolution process. So we save those responses in our cache, and that way that limits our need to go out and discover that information again, essentially. That information will be stored in that cache as long as the time to live doesn't expire, okay? Now we see listed here in the book, it says when a DNS resolver sends a query asking for information, the authoritative or non-authoritative server, an authoritative server would be one within our domain, and a non-authoritative server would be essentially one outside of our domain, could respond with the DNS query response message with that resource record or the data. And inside of that resource record is that 32-bit time to live field that's used to inform the questioner, the resolver, how long that resource record could be cached before it needs to send a query again requesting that same information. All right. The idea is that this field can be used maliciously by setting the value to a short or long time. You know, short if you want to poison out legitimate entries, or long if you want to maintain illegitimate entries. So the concept of a cache poisoning occurs when the attacker sends fake information, spoofed resource record information to the resolver. The resolver receives that fake information, stores that information in the cache for that particular lifetime, and then we use this technique to basically redirect users from legitimate sites to harvesting sites or malicious sites, whatever their general objective is. All right. Attackers can poison these caches by impersonating name servers, making a request to a DNS resolver, and then forging a reply when the DNS resolver queries the name server. DNS uses UDP typically for these client-based transactions instead of TCP. So there's really no verification for the DNS information. All right, so let's say that somebody says, what is the IP address for Cisco.com? And that information gets sent to the DNS server. And the attacker says, well, I am the authoritative name server for that domain space, and the IP address is 10. Whatever, 192, whatever it might be. All right. And in essence, that information gets sent to the user. That information gets cached. And as long as that information is cached, that user is going to be directed to that malicious website regardless. All right. Now, instead of using TCP, which requires both parties to perform a handshake to initiate the communication and verify the identity of devices, DNS requests and responses use UDP. And with UDP, as we've talked about previously, there's really no guarantee that the connection is open, that the recipient is ready to receive, that the sender is who they say they are, and so on. So UDP is vulnerable to forging attacks for this particular reason. I can send messages via UDP and pretend it's a response from a legitimate server by simply forging the header data. All right. If a DNS resolver receives a forged response, it will accept that information and it will cache that information because there's really no way to verify if the information was accurate, if it comes from a legitimate source, and so on. They do talk about that a little bit right here in this section about the DNS Transaction ID and how the DNS Transaction ID doesn't have enough entropy, meaning that there's not enough randomization to the process. There's a 16-bit field in the header of one of those sections. We talked about the different sections of the DNS header that allows us to identify that particular transaction, and we kind of marry that with the port that's being used, the source port that's being used in the request. But as an attacker, I can simply analyze those transaction ID values, and because there's not enough entropy in the process, I'm basically have the capability of predicting what those valid transaction IDs would be, or the future transaction IDs would be, and based on that understanding, I can actually spoof a legitimate DNS response or DNS message with the correct transaction ID, even though it's fake information, even though it came from me as the attacker. The individual that queried the request or sent the request initially is going to accept that information. That resolver is going to accept that information, which means now that the cache is poisoned. All right. Now, let me just say that despite kind of these points of the vulnerability in the DNS caching process, DNS poisoning attacks are not actually easy to facilitate. Because the DNS resolver does actually query an authoritative name servers, attackers only have really a couple of milliseconds to send that fake reply before there's actually a reply that's sent by the authoritative name server itself. All right. Attackers also have to either know or guess different aspects or factors that are carried out in this DNS spoofing attack. Which DNS queries are not cached by the targeted DNS resolver. So that resolver will query the authoritative name server, what port the DNS resolver is using. They used to use the same port for every query, but now the ports are random. Although, you know, we still fall within that 16-bit field, so we have a limited number of ports that are available to us. They need to know the request ID number. And then the attacker would have to know which authoritative name server to go to. All right. Attackers could gain access to the resolver in different ways. You know, it could be hacks. I could gain physical access to the resolver, and we could alter the cached information that way as well. All right. DNSSEC, in short, which is a DNS system security extension. That's essentially what it stands for, is a means to verify DNS data integrity and the origin of the DNS information. All right, DNS, again, as I said, originally didn't have any of these verification steps, but DNSSEC uses public key cryptography, like digitally signing, to verify and authenticate DNS information. DNSSEC is not really mainstream yet. It's fairly new. I mean, well, it's been around for a while, but I think it was introduced in 2005 or 2004. I think it was 2005. And it hasn't been widely adopted yet, but it will definitely provide additional levels of security. Now, another type of attack that they mention here specifically is the DNS Amplification and Reflection Attack. These types of attacks are made possible by Dns Open Resolvers. In short, a DNS amplification attack is a distributed denial of service attack where the attacker exploits vulnerabilities within DNS to turn initially very small queries into much larger payloads, which are then in turn used to bring down a victim's computer or server or whoever is the target of this particular attack. It is a basic type of reflection attack which manipulates publicly accessible DNS information or DNS, not DNS information, but domain name systems, making them in turn flood a target with large quantities of UDP packets. There are different types of techniques where we can inflate the size of these UDP packets as well, so that these are relatively robust types of attacks. Just like any type of amplification attack, it is a reflection attack. In this particular case, the reflection is actually completed by eliciting a response from a DNS resolver of to a spoofed IP address. The victor, the attacker, sends out a DNS query with a forged IP address of the victim in this particular case to an open DNS resolver, then basically suggesting to that DNS resolver that it needs to reply back to that address with a DNS response. And if I can send out fake queries, you know, a bunch of, or at least a significant number of fake queries, and with multiple DNS resolvers replying back simultaneously, either the computer itself, the victim, or the network can be overwhelmed by these DNS responses. That's the reflection piece of it. But you can also add or incorporate the amplification piece as well, which means that we were sending out relatively small queries, but we're getting disproportionate response packets. To amplify the DNS attack, the request can be sent using a protocol extension, which allows for very, very large DNS messages. That's the eDNS0 extension, I believe, specifically. All right, or we could use some sort of cryptographic feature of DNSSEC to increase the message size as well. If I have a spoofed query with a type of any, that means that I would essentially return all known information about the zone in a single request. So with these different methods, a DNS request message that might be only 60 to 100 bytes can get a response of 4,000, 5,000, 6,000 bytes to the target. So we're talking about an amplification factor of 70 or 80 to 1 in this particular case. That's a significant increase in the volume of traffic that the targeted device gets, and then we can, of course, accelerate that to very quickly bring down a particular client. All right. Now, DNS amplification attacks also rely on relay DNS requests through different botnets as well, which means now we're increasing the volume of the traffic that's directed at the victim, and of course it's distributed denial of service attack, which makes it extremely difficult to identify the actual source of the attack. All right, there are some mitigation techniques that we can use. We can tighten our DNS server security. We can block specific DNS servers or all open recursive relay servers. We can do rate limiting and so on. But there are, we'll talk about some of the tools that are available with Cisco's platforms a little bit later on. All right, so the next thing we're going to talk about is fast flux, double IP flux, and DGA. All three of these methods, or all three of these things, are used by attackers and whatnot to hide their systems or hide malware, or at least their access or direct access to command and control servers, so that mitigation applications and individuals that are trying to locate these command and control servers are easily hidden, or at least very difficult to locate. So let's start by talking about what is fast flux, what is a fast flux network, how does it work, and what is its purpose, right? The term fast flux refers to networks that are used by different botnets to hide the domain names that are used to download malware or that might host phishing websites. We can refer to this type of network as a peer-to-peer network, which is used to host both the command and control centers or proxies that are used by botnets, and the whole point is to make it extremely difficult to find and dismantle those particular networks. All right? The basic concept of fast flux networks is having thousands or tens of thousands or hundreds of thousands of IP addresses that are associated to a particular domain name, and then constantly changing those in quick succession, usually within 300 seconds or so, or 5 minutes. In the case of a specific one, which was called Avalanche, there were over 800,000 malicious domain names used by criminals, and IP addresses changed within, probably about that 5-minute window, between the time we initiated connections to different machines and so on. Most machines that make up this type of network aren't actually the ones responsible for hosting or downloading the malicious content to the victim itself. That basic task is going to be reserved for the computers that act as the servers of the malicious content itself. The rest of these machines that sit within this network simply act as redirectors that help to mask the real address of those particular systems that are being used by these nefarious individuals. And if we wanted to go ahead and complicate this whole process even further, we ensure that those critical systems in the network have the highest amount of bandwidth, the highest amount of availability. We have load balancing systems to handle all the requests. So in essence, they're building in the things that we like to have within our networks to ensure that the networks are going to function. All right, now there are two main types of fast flux networks. There's a single flux network, and then there's a double flux network, and we see those two examples. We'll talk about DGA in a minute. All right, a single flux network has multiple individual nodes that are registering and deregistering their IP address as part of the A record for a single domain name. These registrations are typically very, very short lifespans, 5 minutes on average, to create this constantly changing flow of IP addresses when we're trying to access a particular domain. All right, and we're talking about potentially thousands or hundreds of thousands of IP addresses tied to a particular domain. All right, so that when one of those particular devices drop, another device will simply take over. All right. The domain names that are used are usually hosted on servers that are extremely protected and what we call bulletproof servers, if you will, which means that it's extremely difficult for even law enforcement agencies or these service providers to actually take down the domain that's in question, right? Because that ultimately would be the best way to do it, is to simply get rid of the domain. All right, not go and get rid of the fast flux servers or proxies, but to get rid of the domain. Now, double flux networks use essentially the same components and methods of establishing the communication between the victim's computer and the command and control servers. But in this particular case, the zombie computers are part... Sorry about that. That was my Alexa talking to me. In the case of the zombie computers that are part of this botnet, they're going to be used as proxies. What this does is it prevents the victim from actually interacting directly with the servers that are actually hosting and serving the malware. And again, it makes it extremely difficult to locate these computers. It is just another layer of concealment in this particular case to keep the infrastructure up and running for a longer period of time. And that's ultimately the goal. Now, one of the most important kind of developments, if you will, in the malware space over the past 10, 15 years is something called domain generation algorithm. A DGA is an automation technique that an attacker will use to make it much more difficult for defenders to protect against specific attacks. Now, this is not something that's new, but it is still rather effective, even though it's been around for 10, 15 years or so. All right. The domain generation algorithm is essentially a program that designates or at least is designed to generate domain names in a particular way. All right, we develop these DGAs so that malware can quickly generate a list of domains that it can use for the sites that give instructions to receive information from the malware. These are the command and control or C2 sites, or sometimes referred to as the mothership. The attackers use the DGA so they can quickly switch the domains that they're using for the particular malware attacks. And they do this because security softwares that are developed by vendors typically block or at least take down or at least identify malicious domains that malware use relatively quickly. So we developed, the attackers developed these DGAs to counter this particular action. In the past, an attacker would simply maintain a static list of malicious domains. And as a defender, I could easily take that list, start blocking it, taking down those sites. But by using the algorithm to build this list of domains, we make it much harder for the mitigators to know or to predict what domains are going to be used if we just simply had a simple list of domains. All right. To get the list of domains that the malware is going to use, we would have to decode the algorithm that was used to create those domains, and that's what that's where the difficulty lies. All right. Now, taking down a site that malware is hosted on using the DGA because it is extremely difficult, because you have to go through the process of actually working with the ISPs to take out those domains one by one. But these domains or DGAs are built using hundreds or even thousands of different domains. And on top of that, they're very temporal, right? These domains are only used for a limited period of time. So taking down the DGA-related domains is kind of like the whack-a-mole game in a lot of cases, all right? The DGA can't really harm you. That's not the whole point of DGA, but the idea is to enable malware to evade modern security countermeasures in a lot of the security products that we see today. All right, because DGA is a technique that is used to add fire to the malware attacks, typically we will set into place some very basic security constructs, right? Don't open attachments from unknown sources. Don't enable macros on the attached documents. Run security software that will actually look for signatures of malware and so on. There are some other technologies that are being developed to kind of directly counter DGA-based attacks, and we'll see some of this a little bit later on. But that's the general concept that we're trying to get here. So both fast flux, double IP flux, DGA, just a way for attackers to essentially hide their domain information, or at least change the domain information on a regular basis so that they can maintain their command and control networks, their botnets, and ultimately infect the computers. Which three options are considered DNS vulnerabilities? Yes, a DNS Cache Poisoning attack would be one of those. DNS Amplification and Reflection attacks, and let's see, DNS Resolution Interception, DNS Phishing, TCP SYN Flood. That would not apply because DNS uses UDP, DNS Brute Force Attack, or DNS Resource Utilization Attack. So the only one that really applies here is the DNS Resource Utilization Attack. A brute force attack would simply apply to password guessing attacks or password discovery or crypto variable discovery attacks. Phishing is an email-based attack. Farming might have been an option here if farming was one of those. That's DNS redirection. Resolution interception is not necessarily an attack. Just because I'm seeing the resolution process doesn't mean I'm necessarily manipulating that resolution process. So in that case, that wouldn't be a choice. Why are DNS Open Resolvers the focus of so many malicious activities? DNS Open Resolvers sit inside the firewall, which must pass DNS traffic, making them easy attack vectors. No, Open Resolvers typically sit outside of the firewall. They're on the internet. These servers must respond to any query from any host on the internet. That's absolutely true. All right. Since the DNS Open Resolvers belong to no administrative authority, they cannot be secured. That's not true. They do belong to an administrative authority, just not within your administrative domain. DNS Open Resolvers are used by enterprises, allowing the attacker an easy means to infiltrate the network. No, actually, Open Resolvers are not typically used by enterprises. They're used by people on the internet and so on. All right. All right, the next topic we're going to talk about is DNS tunneling. This has been around for quite some time. It's not really anything new in the realm of security, but we've already talked a little bit about DNS security and what DNS security requires, but let's go ahead and talk about what DNS tunneling is and how does it work. DNS, of course, by definition, is really a fundamental protocol that we use on the internet, and without these services available to us, it'd be very difficult or extremely difficult to be able to find anything that might exist on the internet. We have to be able to resolve these human readable names into IP addresses. So if we want to visit a website, for example, we need to know the exact IP address of the server that's actually hosting that website, which would be impossible without this particular protocol. So DNS traffic is really some of the most trusted traffic on the internet that we see today. We typically allow DNS to pass through our firewall, both inbound and in the outbound direction. Not as much inbound, but occasionally if we're hosting DNS services on our DMZ or Insider network, because it's actually really important for our employees and our users within our enterprise to be able to visit external sites, external websites, and external services and so on. So DNS tunneling takes advantage of this particular fact by using DNS requests to implement a command and control or CNC channel for malware implementations. Inbound DNS traffic can carry those commands to the malware, and then the outbound traffic can then exfiltrate our sensitive proprietary or personally identifiable information, or provide some sort of response to the malware operator's request for some sort of control function. This actually works because DNS is a very, very flexible protocol. There are really kind of very few restrictions on the data that a DNS request actually contains, because the protocol itself is designed to look for domain names of websites, and those domain names could really be kind of anything, right? Since almost anything can be a domain name, those fields that actually carry that information can actually be used to carry sensitive information within those fields themselves. So the requests are actually designed to go to an attacker-controlled DNS server, making sure that they can receive that request and then respond to the corresponding DNS replies. DNS tunneling attacks are very easy to perform, and there are a whole bunch of different tools that are available online to actually facilitate these different types of attacks. This actually makes it really possible for even somebody that doesn't have the skills or the technology or even this, the wherewithal to be able to launch these types of attacks to get data out of an organization or to get data past some sort of network security solution. So given the fact that these types of attacks have been around, or this type of attack has been around forever, how do we protect against it, right? Well, before we can actually do the protection, we need to be able to identify that it's actually happening. All right, and again, the whole concept of DNS tunneling is it abuses the underlying DNS protocol. Instead of using those DNS requests and replies to perform legitimate IP address lookups, the malware uses it to implement our command and control channel with whoever's handling that command and control information. And again, because the protocol is so flexible, because it carries this kind of arbitrary information, if you will, it really doesn't have a whole lot of limitations. All right. Now, there are some things to look for, right? You could look for unusual domain requests, for example. DNS tunneling malware encodes data within the requested domain name field, like put your data in this field .baddomain.com, for example. Inspection of the requested domain names within the DNS request could enable you as an organization to differentiate between legitimate traffic from the attempted DNS tunneling traffic. You can also look for unusual domains themselves. DNS tunneling only works if the attacker owns the target domain, so that the DNS request goes to their DNS server. So if you're an organization and you're experiencing a sudden surge in requests for unusual domains, that could also be indicative of kind of an anomalous behavior, if you will, indicative of some sort of DNS tunneling attack that's taking place, especially if that domain was created recently, right? If it's not a domain that's been established for some time. You can also see maybe potentially this occurring if you're going to have a high volume of DNS traffic, right? The domain name that fits within the DNS request does have a maximum size. It can only hold up to 253 characters. That means that as an attacker, if you're going to exfiltrate a large amount of information, you're probably going to need a lot of large number of malicious DNS requests to actually exfiltrate the implementation or implement some kind of highly interactive command and control protocol response. So you're going to see a spike in DNS traffic. Now, these don't necessarily mean that there is some sort of attack taking place, but it certainly would be anomalous behavior, and you would want to go ahead and investigate and see if it is in fact related to this tunneling process. All right, now to protect against DNS tunneling, you're going to have to use obviously some sort of advanced network threat prevention system. You're going to have to be able to detect and block those attempts of data exfiltration. So the system needs to be able to do some sort of inspection of the network traffic, have some sort of access to threat intelligence information so that we can identify that the traffic is directed towards a malicious domain or malicious content that might be embedded within the DNS traffic and so on. The Cisco Next Generation Firewall has that ability to do that threat detection, and it has those capabilities. Now, I've mentioned a few times throughout this discussion about botnets, right? Botnets have always been, I mean, they've been around for quite some time, but they're much more sophisticated than they used to be. And I did mention a couple of times the CNC techniques, the command and control techniques that are used. Using DNS tunneling is one of those methods, right? We would get some sort of malware, virus, worm, Trojan, and so on that gets isolated or installed on a particular computer, and then it participates in this botnet. Now, the evolutionary path, traditionally it was something that was done with IRC, Internet Relay Chat, HTTP, peer-to-peer communication, but the exploitation of DNS and DNS protocols has always been kind of a key element to this, right? It is, in essence, a protocol that is ubiquitous on the internet. It is a protocol that we see all the time. All right? So we have to understand what the potential damage is for botnets that compromise, our networks. And DNS oftentimes is a protocol that's not necessarily considered. We might look at DNS traffic after some sort of event occurs. Maybe that's part of our overall investigation, our lessons learned, our analysis afterwards, but we don't typically look at DNS prior to that. So it is something that we definitely need to take into account and really focus attention on. All right, remember, the botnet is not just an infection. It is a whole network of infected devices that are operating either inside your environment or across multiple environments. But these are devices that are definitely out of your control. Sorry about that. My Alexa's going crazy here. All right. So it is very important to be able to understand a solution, or to deploy a solution that's going to be able to detect and block these this attempt to do this exfiltration of information. All right. Now, we've already talked about, obviously, what the tunneling is. DNS tunneling, as the book mentions here, has been around since the late 90s, and it's been around for some time. What we're seeing in this diagram is kind of a representation of data that's being exfiltrated from an infected host using specific DNS queries, and the attackers sending commands to the infected host using the DNS responses itself. Most of the time what we're going to see is that the data is being tunneled out over DNS, and it's going to be encoded by the attacker so that it's not easily recognizable as malicious information. And they actually use two different types of encoding techniques, base 32 and base 64 encoding. All right, if I'm tunneling non-DNS data within the DNS traffic, obviously that's not intended. That's an abuse of the DNS protocol. Every type of DNS record, whether it's a null record, a SRV record, a CNAME record, a MX record, or whatever, any of those types of records can be used to exfiltrate this information. TXT records can store the most amount of data, and that's usually what's going to be used in a DNS tunneling implementation. I mean, a DNX TXT record can actually be up to 65,535 bytes long, so that's a hex FFFF. And then the total length is just part of that resource record header in the DNS message itself. The only issue with this type of record is it's not very common to see this type of request. So you could actually look for a lot of TXT requests, and based on that you could identify that a particular type of attack is taking place. Simply blocking those TXT records as a defense mechanism won't work, because it does break other protocols like DKIM and SPF and so on. Now, in the outbound phase, we split that data that needs to be exfiltrated or carried out into different data chunks, and then each data chunk is then placed into the third or lower level domain name field in the DNS query. So for example, in this case, 10101.cnc.tld. All right, there's not going to be a cached response on the local or network DNS server for this particular query, because it doesn't exist, right? It's not a real host. So that means that that's going to get forwarded to the ISP's recursive DNS servers, and then that recursive DNS server is used by the network, used by that ISP, is then going to forward the query to the authoritative name server that's controlled by the bad person, right? The baddie. Right? So this process will get repeated over and over again until we've actually sent out all of the data chunks that are necessary for us to be able to execute the command or exfiltrate the information or whatever. The inbound phase is triggered when the attacker, that attacker's authoritative name server, receives that DNS query from the infected device, and then it's going to send a response again within the DNS query, and it's going to encapsulate the encoded commands in that particular case. That malware that's on the infected device then recombines those fragments and executes the command. If we don't need that two-way communication, the queries and the responses can be excluded, and that makes it even more difficult to be able to identify this particular type of threat. All right. So we actually have a packet capture here that shows us the DNS queries. These DNS queries have credit card information, right? It's encoded. We can see that it is encoded in hex, the 3434303112 ... number. And if I was to convert that to ASCII, it would be representative of a credit card number, 44018154, and so on. Now, we can employ the use of tools that can do this type of interpretation and extraction to be able to identify that information, but you can see how that would be extremely difficult to facilitate. All right, and so this is a challenge for us. We can't simply block the protocol. We have to allow the protocol to function, so it makes it really, really difficult. So countermeasures, as they mention here in the book, monitor the DNS logs for suspicious activities like DNS queries with unusually long and suspicious names, and deploy a solution like Cisco Umbrella. We'll talk about that in a lot more detail in the future here to block DNS tunneling traffic from going out to those malicious domains. All right, let's go ahead and go through our questions here. Which two options are uses for DNS covert tunnels? All right, which two options are uses for DNS covert tunnels? Let's see, modify data in a database. No, we're not actually trying to execute information into a database. We're trying to exfiltrate information. So stealthy data exfiltration would be one of the choices. Issue command and control traffic or to bots on the network would be another one. That would be our inbound DNS. Exfiltration would be our outbound DNS. Denial of service, no, we're definitely trying to capture information. We're not trying to deny service. To send DNS traffic with an IPsec tunnel, no, we're not encrypting or providing confidentiality for the DNS queries. Which two options are countermeasures that an administrator should employ to protect against DNS tunneling? Monitor the DNS log for suspicious activities. Again, that's hard to do, right, if you don't have an adequate baseline of what normal activity looks like. So you want to be able to monitor for anomalous behavior, and that's going to require some advanced threat techniques and threat identification and mitigation techniques. Certainly we can't simply deny all DNS. Encrypting the DNS doesn't really matter because the DNS queries are legitimate as far as the application is concerned. We're just embedding the exfiltrated data within the URI field or the query and whatnot. So that won't work. Deploy a solution such as Cisco Umbrella to block the tunneling traffic, and that would be something that we could do. All right, again, we have a whole section where we're going to talk about Umbrella a little bit later on. All right, so let's move on to our next discussion. We're going to talk about web-based attacks and get into some HTTP and command injection communication as well. All right, in our next section, we're going to talk about different types of web-based attacks. Obviously, the web is something that we need to use quite a bit, pretty much every day, right? We're accessing web resources. A typical attack, they do break it down here. I'm going to kind of go through these bullet points, and then we'll talk about some more specific types of attacks and how those attacks are facilitated. And then we'll get into some of the details later on in this section. But typically, a web-based attack has multiple stages. Number one, we have to go to a website, right? And it's a website that has been taken over or hijacked or otherwise a malicious website that is, or a website that is compromised in some way. And then by going to that website, either we're directly faced with the illegitimate information or we're redirected to another site that's running malicious code that's controlled by a particular attacker. We're going to go through multiple intermediary servers potentially to kind of hide our tracks and obfuscate that overall path that we're using to get to that particular destination. And then we execute these exploit scripts. And there are many different types of exploit scripts that can be used. We're going to talk about some of the most common, probably cross-site scripting or XSS, SQL injection, path traversal, local file inclusion, distributed denial of service, and so on. These are some of the kind of the common types of attacks that you're going to see. These kind of drive-by exploits, drive-by downloads, which are done in the background. You're not actually aware that a download is actually taking place, is based on the fact that you're accessing this particular malicious site, and that malicious site hosts that particular exploit kit. A drive-by download means that the malware that actually infects the computer of the individual is being done simply because they're passing through, right? They're driving by this malicious site. And just by simply passing through, going to the landing page or whatever that contains that exploit, when I get redirected to that site hosting that exploit, the exploit kit then scans the computer of the victim, looks for a particular browser, looks for a particular piece of code or piece of application or whatnot, finds a vulnerability in one of those implementations, and then based on that vulnerability, takes advantage of it, and the exploit kit will use some sort of script to manage that attack and then implement that particular attack. These exploit kits are very difficult to mitigate against because they have so many different forms. They come in a lot of different forms, and they take advantage of known vulnerabilities on the local host that's accessing that particular site. Now, once a particular exploit kit is identified, or that exploit kit has gone through and identified a particular piece of vulnerable software, it sends the request to the exploit kit server to download that particular exploit code that it needs to be used to compromise that vulnerable application, which is why you need to make sure your browsers are updated. You need to make sure that your security settings in Java and other kind of dynamic protocols and applications that you're using on your computer are up to date and secure, because this is not just an attack against one vector. This is an attack against multiple vectors, or potentially multiple vectors based on whatever vulnerabilities exist on that particular client. All right. Now, once that malicious code connects to the computer, the malware gets downloaded in a payload. That payload could be a file downloader that gets other malware, or it could be the final malware that we're trying to install on that computer, and then that encrypted malware, or that malware that gets installed on the computer gets decrypted and executed on the machine. All right. Now, in the 2016 annual security report by Cisco, there was a lot of pressure to remove Adobe Flash from your browsing experience, because there were a lot of different exploits against Adobe Flash and Adobe Flash content. We actually, based on that, removed all of the Flash content from our website as well. And we try to limit the amount of interactive applications that we have on our website. In fact, they actually mention in the book one of the most common, or actually one of the leading exploits, called the Angler exploit. The Angler exploit was one of those leading exploit kits that was used by attackers to distribute and install malware, and it included things like ransomware, banking trojans, ad fraud components, and so on. Just like every other exploit that exists, or exploit kits that exist, their focus is on web-based vulnerabilities in the browser itself and the plugins that exist within that particular browser. Angler was actually one of the few exploit kits during its time that offered what we called a fileless infection, where the malware actually never touches the disk and only resides in the memory, so that it could avoid detection. Now, it hasn't been around for a while, right? I think it was like June or July of 2016. But it was a pretty prevalent exploit, right? Black Hole was really kind of defined as the king of exploit kits, but that disappeared in like 2000, I think it was 2013. Angler started to kind of come into its own. All right. Angler used vulnerabilities in IE, Silverlight, Flash, Adobe, Java, and a lot of other applications to actually implement its infection, or to facilitate the infection. All right. Angler also made use of, and this is pretty common with a lot of different types of attacks, Diffie-Hellman encryption key and key exchange process and encryption keys to make every single attack unique to a particular victim. All right. So if somebody was doing a packet capture or whatnot, that would make it extremely difficult to replay that packet capture because it was unique to that particular host. Angler was one of the most technically complex exploit kits that we've seen. All right, there was a lot of imagination and integration in this application to facilitate the attack. And it was also very good at introducing new exploits for unpatched vulnerabilities, what we call 0 days, right? 0-day attacks. So it became a real problem, all right? Traffic that went to the Angler exploit kit came from malvertising and compromised sites. So, ad intensive sites and so on. The redirection is basically a really important part of the entire exploit kit process. There have to be close ties between the operators and the exploit kits themselves to implement these different infections. We did the drive-by download. We're browsing to a legitimate site or a compromised site for that matter. We get redirected to the exploit kit page without any sort of action on the part of the user, and that redirection actually could even happen in the background. We could do that via iframe, making the infection process practically even unnoticeable to the user itself. If the user was vulnerable, or if in some cases or a lot of cases there was some sort of 0-day, the malware was dropped onto the disk or injected directly into the memory of the computer, and then that would be our delivery mechanism or vehicle for the subsequent malware infections. So what we're seeing in this particular diagram here is how attackers use WordPress servers in their ransomware attacks. The victim is going to browse to a compromised website that has banner ads, what we call malvertising. I mentioned that term briefly previously, and exposed the victim to the exploit kit. That exploit kit found the vulnerability in the Flash player of that the victim was running. That Flash exploit code then gets downloaded from the exploit kit landing page to the victim's computer. That Flash player is now compromised, and the victim's computer is now running that malicious code. That malicious code then in turn downloads the CryptoWall malware to the victim's computer from the malware downloader server, which is probably going to be a different server which is hosting than the one that's hosting the exploit kit landing page. That CryptoWall malware gets executed on the computer of the victim, and then it connects to the command and control server to get some sort of encryption key. We talked about the Diffie-Hellman exchange process that was utilized with Angler. The CryptoWall malware encrypts the data with that retrieved key on the victim's computer, reports the encryption status back to the command and control server. The command and control server then sends the victim that ransom notice, payment site information, and so on. All right. Now we're talking about, in this particular case, an attack in which we're installing ransomware, obviously encrypting the user's information, and then holding that for ransom. All right. Now, what are some of the countermeasures that I can implement? I can obviously identify malicious sources of information. I can block redirection. I can make sure that I have a limited access to these applications and plugins in my browser. Right? We need to make sure that the web applications are secure using OWASP. Best practices. OWASP is one example of kind of a consortium of security professionals that identify basically what are best practice techniques and standards that I can use to secure applications. The Open Web Application Security Project. Make sure my browser's up to date. Make sure my operating system is up to date. It's not going to protect against 0 days, right? We still have to concern ourselves with 0 days, but it will protect against some of the more kind of common drive-by download exploit kit locations, right? Or at least the ability for the exploit kit to identify a vulnerability and implement some sort of attack based on an open attack vector based on those vulnerabilities. Use Umbrella. Again, they mention Umbrella here. We're again going to talk about Umbrella. Deploy a web proxy solution like the WSA appliance, which we'll talk about later on in quite a bit of detail, to block users from accessing those malicious sites. So even if the redirection occurs, that redirection is going to be blocked. Deploy a web proxy, educate your users on how web-based attacks occur. Now, I wouldn't agree necessarily that this is probably one of the better options because, again, you may not even have time to identify that this is happening, right? It could be happening in the background with iframe, or it could happen so quickly that you wouldn't even be able to identify that it's occurring. Yes, certainly you want to make sure that users are aware that this type of thing could happen, but really we need technical controls or logical controls to protect against these types of attacks. Which two statements about malvertising are correct? Malvertisements are sometimes set up to affect all visitors to a site only during a specific period of time. We didn't actually talk about that, but that is absolutely true, right? It may be that you've identified that users during the day typically are business users, or they're users that are working from a corporate environment, and we know that those tools are in place to protect against those types of attacks. And to limit the ability of organizations to identify these attack vectors, we might decide to do it at night when it may be just kind of private browsing from your personal computer at home and you don't have all those controls in place. So I didn't mention that specifically, but that could be one of the choices. I'll go ahead and check that one. Let's see if there's some other. Malvertisements, malicious code remains forever. No, that's not necessarily true, right? The idea is that we infect the machine. Maybe the malware stays on the computer, but the malicious code, that drive-by download code, is what allows us to execute the exploit script and the exploit kit to be able to install the malware. So it's typically not there forever. Malvertisements affect both trustworthy and untrustworthy sites. Absolutely. Absolutely. Infections only occur when the victim clicks the malvertisement. No, it's not true, right? Depending on what's embedded in the application and depending on how the malvertisements are applied will depend on whether or not something can occur in the background. Malvertisements are not a security concern. Well, of course, they're absolutely a security concern. Now, I want to be clear here. There's a difference between malvertising and ad malware, right? Malvertising, we kind of confuse those a little bit. Ad malware or adware, it's another way, obviously, of affecting your browsing experience and so on. But adware is basically a program that's running on a user's computer, all right? It could be packaged with a legitimate piece of software or installed in the background without the user's knowledge. Adware basically displays unwanted advertising. It might redirect search requests to different advertising websites. It might even be used to mine data about the user to help target or serve advertisements to that particular user. But there are some differences between malvertising and ad malware. Malvertising involves malicious code, all right? And that's always going to be initially deployed on that particular publisher's web page. Adware is only used to target individual users. Malvertising only affects users that are viewing those particular infected pages, where adware, once it gets installed, operates continuously, all right? And malvertising could facilitate attacks in multiple ways. We already talked about the drive-by download, right? The installation of malware or adware on the computer that happens to be visiting that particular ad or visiting that website. And that's made possible due to vulnerabilities in the plugins in the browser and vulnerabilities with the browser itself. We could do a forced redirect to another browser that is malicious, or we could actually use it to display unwanted advertising, pop-ups, and so on, beyond what might be legitimately displayed by the ad network that's tied into that particular site. And that's done by using JavaScript. If we actually click on the malicious ad, that could execute the code, that could install the malware, adware on the computer. It could redirect the user to a malicious site that's very similar to a real site, facilitating some sort of phishing attack, and so on. All right. We have lots of delivery mechanisms to insert malicious code. We could do ad calls, where a website displays a page that contains an ad, and then that ad exchange pushes ads to the user through different third parties, and then the third party servers could be compromised by the attacker. We could do injected post clicks, where the user clicks an ad, and then they're redirected to several different URLs, ending with an ad landing page, perhaps. We could do it in the ad creative. Malware can actually be embedded in the text or the banner ad. So in HTML5, for example, it's possible to deliver an ad as a combination of images and Java, which that Java could then contain that malicious code. Or you could deliver it in flash.swf format and so on. We could do malware within a pixel. Pixels are code basically that's embedded in the ad call or landing page, which sends data to the server for tracking purposes. Legitimate pixel only sends data, but if an attacker intercepts that pixel's delivery path, it can actually send a response containing that malicious code to the user's browser. We can also put it inside of video content, inside of a flash video, on a landing page, and so on. So there's lots of different options there. All right. All right, let's talk about HTTP 302 cushioning. This is another type of exploit, often called a cushioning attack, that is a redirection attack. We talked a little bit about redirection when we talked about the Angler exploit kit. That, again, was one of the most prevalent and advanced exploit kits that showed up recently and is actually kind of continually evolving. We talked about how the Angler continues to utilize things like malvertising to push landing pages and malicious actors that are still registering domains solely for serving exploits within the enterprise, or within the internet, I should say. But we also see an increase now on two new infection vectors, 302 cushioning and domain shadowing. So we're going to talk a little bit about what 302 cushioning is in this particular case, right? 302 cushioning, or what we would simply refer to as a cushioning attack, is used to redirect the victim to a malicious site without the use of a more traditional technique, like hidden iframes or external script SRC tags and so on. We actually use HTTP 302 redirects over iframes to evade detection by your traditional signature-based IDS and IPS engines. Now, this technique is not new. It's actually been around for quite some time, almost 10 years or so, right? I think it came out somewhere around 2012, 2013. Domain shadowing, which is actually an idea that was coined by Cisco, involves compromising a parent domain and then creating multiple subdomains that point to that particular malicious code. That means that in the majority of cases that we see, the victim's hosting account credentials are actually compromised in this particular case. And these subdomains can be created and deleted quickly, making this a really, really kind of popular technique for bypassing domain and URL block lists that might exist out there. All right. Now, these developments are kind of notable since they actually show this ever-evolving approach to exploit delivery, which is what we have to deal with when we are dealing with malware and threats that exist within our enterprise. Angler has been used many, many times for things like obfuscation, encryption on landing pages, and then payloads that get delivered combined with cushioning and domain shadowing. And Angler just simply adds yet another layer of stealth for defenders to counter, basically. All right, now the exploit cycle in this type of attack typically starts with a compromised website, followed by a 302 cushioning attack, and then a domain shadowing leading to the exploit kit hosting site that we're trying to direct the user to. So we have some sort of compromised website, which leads to a 302 cushioning attack, and then we have domain shadowing, the exploit kit landing site, and then finally the malware payload. Now the book goes into a description. It says a website can change the path that is used to reach a resource by using a redirect option. All right, that's where the 302 concept comes into play. And that redirect is used to effectively tell the user's browser what the new location is for that particular page. The 302 found HTTP response status code is used for this particular purpose, right? And that response status code is really just a very, very common way for us to actually perform URL redirection. It's built into the protocol, right? Oftentimes, a lot of these different types of attacks that we see within an enterprise are based on, like the DNS attack that we talked about previously, the DNS tunneling attack, are based on taking advantage of the functionality that the protocol already provides. All right? So an attacker is going to use a legitimate HTTP function, like these 302 HTTP redirects, to carry out their attack. So we need to understand from a security practitioner and from a security professional standpoint how a function like HTTP redirection works and how it can be used during a particular attack. Now, as far as the HTTP response status code 302 found is used, it was defined quite some time ago. I think it was RFC 1940 something, 1945, I believe, was that initially defined that code. But basically, it gives us a description phrase that the page you're trying to access has moved temporarily rather than found. Now, this HTTP response with the status code provides a URL in the header field location. And this is basically an invitation for the user agent, which is your web browser, to make a second, almost identical, if you will, request to the new URL that's specified in that particular location field. And the end result of this action is that we're going to get redirected to the new URL. A lot of browsers actually implement this code in a way that actually violated the standard that was defined, changing the request type of the new request to a GET request, regardless of the type employed in the original request, which was typically going to be like a POST request. All right. So there are some additional status codes that are created, like 303 and 307, to kind of identify the difference between the different behaviors. All right. So subsequently, a common type of attack or a common technique that's used by the attacker to avoid detection is to kind of hide or obfuscate the source from where the malware was downloaded by using these different web redirections. We can use that legitimate 302 found response to create a series of web redirections, before the victim's browser gets finally redirected to the page that actually delivers the exploit to the victim's computer. These intermediate sites are called gates. And the idea here is that we're using these gates, and we're changing the URLs of these gates frequently within an hour or a half hour or whatever, to deprive the security practitioners, the subject matter experts that are out there trying to identify these threats and be able to publish these threats, from actually getting enough time to come up with an attack analysis, and then consequently or subsequently coming up with a way of blocking these redirects from taking place. It adds basically this extra layer, which makes it much more difficult to find the source of the malware. It's kind of like those FBI shows or those criminal shows where the criminal is trying to break into a bank or trying to place some sort of fraudulent call or whatever, and the idea is that you're going through all these different nodes around the globe. You got the little graphic that shows all the little dots around the planet that you're connecting to. So if somebody's trying to trace a call or whatnot, it makes it extremely difficult for them to identify where that particular host is or where the source of that attack is, because we have to go through so many different locations to identify it. And as I mentioned when we kind of started this discussion, the use of the HTTP 302 redirections gets rid of the need for us to use iframes or external scripts, because the redirections are less likely to raise any kind of suspicion compared to some of these other techniques, particularly external scripts, which are easy to identify and relatively easy to block for that matter, right? An iframe, maybe a little bit more difficult. Iframes are basically components of HTML that allow website developers to load another page as needed as well. All right, so what you're seeing in this particular diagram is an example where the attacker compromised a legitimate website. They generated this 302 found HTTP response to the victim's computer, compromise.example.com/index.php. That then triggers several different HTTP 302 redirects through the different proxies before the victim's browser finally gets redirected to the attacker's web page that's actually ultimately going to launch the exploit and install the software on the computer. All right. Now, whether you decide to use iframe or 302 cushioning, obviously we understand what the overall objective is, right? Serve the malicious exploit to the victim, be able to install the software so that we can then further control that particular computer. Now, we do actually see a HTTP 302 Wireshark capture here. We can see the highlighted components. The full cycle from the victim site to the successful exploitation this is where it started, right? We see the HTTP 302 moved temporarily, and then we see the location, that long URL that's listed there. All right. Then we can see in kind of as the next progression, right? That 302 cushioning accesses the victim's site. Then we have a different type of code that might get installed, and in this, one of the common ones that you see listed online would be like an Angular landing page, and then you might see some subdomain changes between different sessions. Indirect exploitation, also very similar to direct exploitation methods, but an indirect exploitation occurs after the domain is accessed that utilizes remotely hosted content. But once that content is accessed, there is a similar 302 cushion to the final exploit domain, and then we can install the software based on that. Now, there are some mitigation techniques that we can use to protect against 302 cushioning. Of course, they do mention the use of Cisco Umbrella to block users from accessing malicious websites, but that would assume that we already understand who those malicious actors are and we're able to identify that, which is not very easy when it comes to this particular type of exploit. We can also deploy a web proxy solution, WSA, but again, we are basing that solution on the fact that we're aware of these different redirected URLs, and we're able to block them based on the based on the reputation score, based on our understanding that these particular domains are not authorized, right? We can certainly execute. Yeah. We don't want to do that. We want to educate our users on how redirections work. But again, it's not like a user's going to be able to identify quickly enough that a redirection is taking place and they're going to shut down their browser or whatnot. So it is, we can certainly educate the users on what to look for. If they see those particular transactions or they see those symptoms, they can at least report that those events are taking place, and we can make sure that they haven't been infected or make sure they haven't been compromised. You could do other things by adding like metadata values, like don't redirect, or you could say, stop redirecting for 302. But that has to do with the actual design of the site or the code itself. There could be other mitigation techniques as well, but most of it has to do with the ability to identify that an exploit kit is being deployed, that malware is being deployed. Even though the redirection occurs, we should still be able to, with our advanced malware protection techniques, prevent the actual infection from taking place. And that's really where the protection is going to come in this particular case. So when we're dealing with these gates and these infections with these compromised websites, and then the 302 redirection. I mean, 302, frankly, is really part of everyday life on the internet, right? And this is kind of what we talked about when we talked about DNS. When you're dealing with DNS, it's not like you can just not use it. It's just something that has to be used when we're dealing with browsing on the internet. 302, HTTP 302s are part of everyday life on the internet as well. So again, attackers are making use of these techniques because we know that these features are going to be available. All right. So a 302 redirection would lead to some sort of landing page, and it might contain a bunch of obfuscated scripts. After that landing page is delivered, the browser or the plugins might get probed for some information, and then we return data to the malicious server or the exploit page, and then we can deliver the payload. All right, so it really depends on mitigating this particular type of attack. Depends on how you're securing your browser. Make sure the browser's up to date. Make sure your operating system is up to date. Make sure you have adequate security settings within your browser. And this could be part of the education piece, right? Identify to your end users that, hey, if you see a pop-up that says potentially unwanted software or potentially dangerous website, or instruct them not to click through if they have that particular option, so that we can protect ourselves, right? We might get to the exploit page. We might even get to the payload session where the exploit kits are dropping various payloads, ransomware, variations of ransomware, and so on. But we still have, again, multiple layers of security that we need to implement to protect ourselves. Is the malware going to be successfully installed? Is it going to be successfully executed? Is it going to be quarantined? If it is installed and executed, how do we protect against the damage or mitigate at least most of the damage from that particular piece of malware functioning on the end user's computer? All right, so our first question here, what happens to the victim's browser during an HTTP 302 cushioning attack? The browser is redirected to the malicious website that delivers the exploit to the victim's machine through a series of HTTP 302 redirections. That's absolutely exactly what it is. We don't even have to really look at the other choices because that, by definition, is what an HTTP 302 cushioning attack is. All right? What is the functional purpose of the HTTP 302 response code? Alert users that an attack is underway? No. In fact, it really doesn't have anything to do with security. It is really just a function of HTTP to allow us to do redirect if a page is temporarily moved. Identify a temporary URL, redirection for a website, and redirect the users to that particular website. That sounds about right. It's not used for authentication, and it's not used if a web page is no longer available. We use a 404 code for that particular purpose. All right? So the next type of attack that we talk about is a command injection. A command injection attack has a goal of execution of arbitrary commands on the host's operating system through some sort of vulnerability that might exist within that particular operating system. It could be a vulnerable component of the OS, it could be a vulnerable application, but some way that allows us to execute arbitrary commands. Command injection attacks are possible when an application passes unsafe user-supplied information. Could be a form, it could be a cookie, HTTP headers, etc., to the command shell, to the system shell. And in this attack, the attacker supplied operating system commands then would get executed with the privileges of whatever that vulnerable application has. So we're inheriting essentially the ability of that application, and we're basically running or executing these commands based on that application. All right. Probably the biggest thing that leads to the ability or the possibility of doing a command injection is insufficient input validation, making sure that the information that's going into the application is formed correctly, formatted correctly, contains the appropriate information, and is not malformed or misused. All right. Now, this type of attack does differ from code injection. Code injection allows an attacker to add their own code that gets executed by the application. With command injection, we actually extend the default functionality of the application, which then allows us to execute system commands without actually injecting the code into the application itself. All right. Now, they do talk a little bit about some of the some examples here, right? Cat wrapper script will output only the contents of the requested story.txt file. So it's just a Linux application that allows us to see the contents of the story.txt file. But by adding a semicolon followed by another command, ls in this example, which is a list command, we actually can then execute the ls command with the cat wrapper script with no issues, no errors, right? So we're still seeing the contents of story.txt, but we're able to actually execute the command of ls, which normally I wouldn't be able to do if I was just basically a basic user that was accessing the system and so on. All right. Remember, the command cat basically prints the contents of a file to a standard output, but it is also injectable. All right. Now, used normally, it's simply going to output the contents of the file that we're requesting. But in this case, we have basically been able to set our privileges to a higher privilege level than a standard user with this arbitrary command that normally would only be able, we would only be able to execute this command with that higher privilege. All right. If we had set a higher privilege to cat wrapper, that's what the result would be. Now, if that wasn't the case, if we didn't have that higher privilege, then this particular command injection would not work. It would not work. All right. We might have a program, for example, that accepts a file name as a command line argument and then displays the contents of that file back to the user. All right. That program gets installed as a set UID root because it is actually intended for the use as a learning tool to allow you as a system administrator in training to inspect privileged system files without giving them the ability, or giving you the ability, I should say, to actually modify those files or damage the system itself. All right, now this particular program runs with root privileges as an example. So the call to the system also executes with root privilege as well. So if a user specifies a standard file name, the call works like it's supposed to work. But if an attacker passes a string in the form of, whatever the attack is, all right, rm-rf / or whatever, or /, excuse me, then the call to the system fails to execute cat because we don't have enough arguments, but it then plows on and goes into recursively deleting the contents of the root partition in this particular case. RM is a remove and -rf and so on. All right. Now, in terms of how we can use this for exploitation, it's possible to allow added characters or added arguments or added strings without any input validation in some cases, and that's what we're taking advantage of in this particular case. All right, here's an example that uses a command injection in an HTTP request. If I want to view a file in a web application, the file name is often shown in the URL format, and this is a normal URL, HTTP, whatever, example.com, sensitive, cgi-bin, userdata.pl, $doc equals user1.txt. Pretty straightforward. All right, but I'm going to modify the URL above with command injection that executes the /bin/ls command, meaning that we're going to list the contents of that particular file. Another example that we see here adds a semicolon to the end of the URL for a PHP page with the cat command. And that means that we're going to be able to see the etc.password file content as well. All right. Input validation, as I said, is probably the most important element to protect against this, making sure that whatever application is being called or whatever information we're trying to access, we are able to identify whether or not the data is formatted correctly and the data is passed through the application correctly. All right. There are many different examples of command injection. Of course, it does assume that we have the ability to perform command injection based on the platform and based on the application. All right. Now, we've been talking about application command injection, but it's really no different than OS command injection, what we would typically refer to as shell injection. This is also a web security vulnerability that allows you as an attacker to execute arbitrary OS commands on a server that's running a particular operating system. And again, this could be done through an application or it could be done through the OS itself. Let's say, for example, they have another example here, and I'm going to go through that example in a second. But let's say, for example, I have a shopping application, right? And that shopping application lets a user view whether an item is in stock in a particular store. And we might actually go in and put in a URL and say, hey, what's the status of this stock? Here's the product ID, here's the store ID. And that would be part of the URL that's being posted to the web server. All right, so we have to query different types of systems. And we have to maybe call out a shell command that identifies the product ID, that identifies the store ID, and we would do that as an argument. That command then outputs the stock status for that item, which then gets returned to that particular user. Since the application implements really no defense, we're assuming in this case, there's no input validation, there's no defense against OS command injection, the attacker can submit another input to execute the arbitrary command. All right, so maybe it's an echo command, right? And we might actually be able to identify whether command injection is even possible by using something like an echo command. All right, so we might say, okay, give me the stock information, but echo A, B, C, D, right? I might see that in the output. Now, an echo really just gives us a supplied string. Well, we supply the string, and then that string gets echoed in the output, but it is an easy way to test for OS command injection. We would typically use an ampersand character as a separator. So we have essentially multiple commands that we can implement. So we could say, give me the stock report .pl, ampersand echo whatever, ampersand store number, right? And we can see that information. So the output will depend on, you know, whether or not the command injection is ultimately allowed. All right. Now we do have some other commands that are useful for OS command injection. It is kind of useful to execute some initial commands to get information about a particular system that you may have compromised, or the attacker may have compromised. Things like who am I, uname, ifconfig, netstat, ps to see processes running on the machine, and so on. All right. Now, certainly the most effective way to prevent OS command injection or application command injection is to never call out two OS commands from your application layer code. But that would mean that you would have to be the one designing the application for that particular purpose. It is, if it's unavoidable, if you have to call out OS commands within, based on user supplied input, then input validation has to be performed. You might have a whitelist of permitted values that you can match against. You might be validating that the input is a particular format, like it's a number or whatever. You might be validating that the input contains only alphanumeric characters, no other types of syntax or white space. But input validation is really the way that we can mitigate the potential harm that comes from this particular attack vector. All right, so here we see a %3b and %20. These are Unicode representations of an actual character. The %3b is in this example right here, the %3b, as you know, in the URL format here, represents the semicolon, right? So we're putting that right there. And the %20 represents a space. Unicode is basically an easy way for us to represent individual characters, and we have a specific Unicode for each individual character. All right. Now that PHP code, we also have PHP code that can be embedded in an application. That PHP code embedded would give us the ability to execute commands as well. Here's an example of a PHP script. The PHP script is called by the web browser. That web server then executes that script and displays CCNA rules in the web browser. All right, just some different examples. There's lots and lots of different examples of this online. But again, how do we mitigate against this? Command injection attacks occur when unsanitized user input is passed and processed. So to prevent command injection attacks, developers should follow best practices to perform user input validation. All right, and I've mentioned that a couple of times already. Which statement correctly describes the theory behind the command injection attack? The goal of command injection attack, the goal of a command injection attack is to exfiltrate data on the web server's operating system via vulnerable web application. No, we're not trying to take information out. I mean, certainly that could be a result. That's not the overall goal of a command injection attack. The goal of a command injection attack is to execute arbitrary commands on a mail server. No, this is an attack against applications within a computer, a host, right? So it's not specific to mail in this particular case. The user enters arbitrary commands on the web server OS via a vulnerable web application. Now that might sound like a viable answer. We did talk about executing arbitrary commands, but again, it's not specific to a web server. We're delivering the information through a web interface, potentially, but it's not necessarily a web server. The goal of a command injection attack is to execute arbitrary commands on the web server's OS via a vulnerable web application. All right? And how is that different than what we saw previously? The user enters arbitrary commands on the OS. No, we inject it. We inject it as part of a regular component, or part of a regular request, I should say. All right, so that's the difference between the two. But again, it doesn't necessarily have to be that specific web server, although typically that's what's happening in this particular case, because that's how we're delivering the information through a vulnerable application on that web server itself. So D would be the best answer in this particular case. So let's talk about SQL injections or SQL injections as another type of threat vector or attack vector that exists. A SQL injection is an attempt by an attacker to upload SQL commands or SQL commands to a website in order to be able to manipulate the data on the server itself. Now, typically the objective of a SQL injection attack is to steal data, to destroy information, or to manipulate data for nefarious purposes. It could be to commit fraud or to manipulate information to be able to do other things on that particular system. The most common method is to actually enter SQL commands into a web form. There are actually many different ways to inject SQL into a web server. You could append commands to a URL. You can inject them into an HTTP post. You can insert commands into a browser cookie that's used by the website, and so on. Now, why are SQL injections so important, right? SQL injections have been the top, essentially, of every top 10 list for many years in the OWASP top 10. Many web applications use databases for storing and retrieving data. Our own website uses a MySQL database to store a lot of the information that we provide on our website as well. But this means that databases contain a lot of important information and potentially sensitive information. It can house things like usernames or passwords, personally identifiable information like date of birth or social security numbers, and so on. Web applications actually interact with the database layer using SQL queries. And these queries get performed by using inputs into the web page, like a search query as an example. All right. If you have a poorly designed web application, it may actually accept any type of SQL query in the input box, but it's only intended to accept a specific type of data. So maybe you're only allowed to put in the user's first name. So attackers can exploit this flaw by entering SQL queries into the input box to retrieve or corrupt data that's stored in the database. The book here does mention the OWASP top 10, as I mentioned. We need to recognize those SQL queries. We need to be able to identify whether or not those SQL queries are in fact malicious, and that will provide us the ability to identify these SQL injection attacks. All right. So here's an example, or a simple example, of a web server with a login page and a SQL backend to authenticate the user. A normal SQL query might look like this. Select the user ID from users, where the username is admin and the password is whatever the password is. Admin and that password field get provided by the user when they actually authenticate to the page. That SQL server then goes to the database, it looks for that information in the database, and it finds those credentials to try to match to a particular user. Of course, if we can't find those credentials, then we simply don't authenticate that particular user. The same query gets applied here with a SQL injection, select user ID from users where username is anything or 1 equals 1 and password equals hack the planet. So if we see a string like 1 equals 1 or a space in an HTTP form response, what should we suspect? The first part of this particular query, select the user ID from users where username is equals, that's hard-coded. That's part of the syntax, that's part of the argument that's actually processed by the web page to be able to process that information. It doesn't matter. We're not actually trying to modify that particular information. We're trying to modify the variables that are passed through the execution of that SQL query. So we provide the bold parts, right? Anything, meaning that we don't really, we're just going to match anything, or 1 equals 1 means that we're overriding that username check. And because we use the OR option, we're actually using a Boolean logic that says, you know, it could be one or the other. All right. And then the last part is the password. Because we did 2 dashes, and a space between the 1 equals 1 and the and, that means that we're basically commenting out that portion of the argument. So even though we did type in the hack the planet in the password field, the password's not going to be actually processed by the SQL server, and it will be ignored. All right. Now the result of this particular query will depend on what we're doing in order to protect the information in our database. Now we'll talk about in a minute what can we do to protect against these types of attacks. But essentially what happens in this particular case is whichever user shows up first or whichever user is authenticated first, we're going to find that as a match, and that's typically going to be a administrator or something like that. Now, we could spend literally hours talking about different types of SQL injection attacks, what are the different techniques and so on. That's not the goal of this particular class. The goal of this class is to understand in general what some of these different types of attack vectors are. Certainly you can go out and look for more research and do more research on these different types of attacks. This is just an example, right? Here's another example where we have a SQL query entering 1 equals 1 with a dash space in the name field, and in this case, and blah is the password. So we're using a SQL query. All the account data for all the accounts in the database will get extracted based on that 1 equals 1 or ignore option. So we're seeing the admin information, we're seeing Adrian, John, Jeremy, and so on. All right, now there are lots of different techniques that we can actually use to limit the ability of the attackers to directly steal or corrupt the data. Most techniques are intended to minimize the ability of the end user to supply data or commands that can be interpreted by the web server or the database. But it's very important to understand that this input can come from a variety of sources. It could come from posted form submissions, URL arguments, browser cookies, and so on. Some of the more common SQL injection prevention techniques include sanitization. This is really a common practice or protection mechanism to sanitize all of the user-supplied data to remove character strings that could be executed as SQL commands by the interpreter or passed directly to the SQL database. Sanitization basically involves replacing executing commands found within the user data with alternative non-executable information or non-executable characters. We can also do filtering and data validation. All the user-supplied data needs to be validated by limiting the format of that data, the length of that information, different attributes or permission inputs that are available. If we do see occurrences of SQL commands or other malicious code, we would then have an argument or have a process to be able to filter that information out. We need to avoid unsecured URL parameters. Avoiding using URL arguments, like in an object relational model, or ORM, that trigger database operations, helps us, right? Instead, we might use some sort of secure API for all of the database access. Limit the scope of the SQL commands as well. Use limit commands within the SQL operations to minimize the disclosure of data in case a SQL injection actually reaches your database. These are pretty common methods or common implementations that we can implement when we have a back-end database. And that all has to deal with how we encode or code our system, right? Now, careful coding doesn't necessarily guarantee protection, so we could have other mechanisms, again, defense in depth type of approach, to protect our systems from these types of attacks. Now, the book here says countermeasures include the following. Application developers should follow best practices. Those are some of the practices that I kind of listed off there. Input validation, constraining the information, sanitizing the information or user input data, deploying an IPS to do application layer inspection or payload inspection to look for malicious SQL injections can work as well. All right. Which two results are required to make a SQL injection possible? A, the application is poorly programmed. Absolutely. If, like we just mentioned, if we don't do any of those protection mechanisms, the sanitization, the input validation, the appropriate programming, we're going to make ourselves vulnerable. User input was sufficiently validated. That's the opposite, right? That's a good thing. Strict security measures were followed when developing website coding. Again, the opposite. That's what we want to do when we're implementing the coding of our website. User input was not sufficiently validated is the other choice here. Again, that's what we want to do. We want to validate the information that's being inputted. And the web server operating system has not been patched. Now, again, we're not really talking about attacking the operating system in this case. We're actually talking about exfiltrating or attacking the information that's stored in a SQL database. So patching the operating system wouldn't necessarily help with that. All right. Now, another type of attack is a cross-site scripting and request forgery. Cross-site scripting, or XSS, is a client-side code injection attack. The goal here, and the attacker's goal, is to execute malicious scripts in a web browser of the attackee, the victim, by including malicious code in a legitimate web page or web application. The actual attack occurs when that victim goes to that web page or that web application that actually executes this malicious code. The web page or the web application becomes the transport mechanism to deliver that malicious script to the user's browser, and then we manipulate the vulnerabilities of that host to be able to further facilitate the attack, right? Vulnerable vehicles that are commonly used for cross-site scripting attacks are things like message forums, message boards, web pages that allow commenting, and so on. So if we have a web page or a web application that is vulnerable to an XSS, it is used, it would be vulnerable because it uses unsanitized user input in the output that it generates. So this user input has to be parsed by the browser. The XSS attacks are possible in things like Visual Basic Scripting, ActiveX, Flash, or even CSS type of information that we use to build our web pages. There are JavaScript is probably the most common implementation of XSS because JavaScript is fundamental to a lot of different browsing type of scenarios, right? And it is a command injection web-based type of attack, as I mentioned. We use that malicious script to inject otherwise, benign or safe information. All right. Now, is cross-site scripting the individual user's problem? If I'm an attacker and I can abuse the XSS vulnerability on a web page to execute some sort of arbitrary JavaScript in the browser, the security of that vulnerable website or that vulnerable application, and the user has been compromised, right? So XSS is not a user's problem like other security vulnerabilities that we've talked about. It affects your users. It's going to affect your enterprise, because we can take those vulnerabilities that exist on these systems and use that to pivot or attack other systems in the enterprise. All right. We can actually see cross-site scripting used to deface a website instead of actually targeting an individual user. We can use those injected scripts to change the content of the website, or even actually to redirect the browser to another page. And then that page would contain an exploit kit or some sort of malware or malicious code. All right. If I have JavaScript, we talked about JavaScript being kind of one of the primary transports or mechanisms. These XSS vulnerabilities are generally perceived as less dangerous than what we just talked about, the SQL injection vulnerabilities. The consequences of the ability to execute JavaScript on a web page doesn't necessarily trigger kind of this, immediate response, right? Fear of possible damage or loss or whatnot. Most web browsers actually run JavaScript in a pretty tightly controlled environment. JavaScript has a limited access to the operating system and the files, but JavaScript can still be dangerous if it's misused as part of the malicious content, right? So malicious JavaScript has access to different objects that the rest of the web pages have access to. This includes things like users' cookies, and cookies are often used to store session tokens. If an attacker can obtain a user's session cookie, they can then impersonate that user, perform actions on behalf of that user, and gain access to other sensitive data. So directly, it's not much of a concern, but indirectly, it becomes a pretty serious concern. JavaScript can read the browser DOM. We can make modifications to that. This is only possible if you have a page where you actually have JavaScript running. We can use an XML HTTP request object to send HTTP requests with arbitrary content to arbitrary destinations. And in modern browsers, if we're using HTML5 application programming interfaces, we can gain access to geolocation information, to a webcam, to a microphone, or even specific files from the file system itself. Most of these APIs do require some sort of triggered opt-in, but we can use social engineering to get around that restriction. All right. So if I use various sets of tools, or I use various sets of methods, I can actually pull off pretty advanced attacks. Cookie theft, planting Trojans, key logging, phishing, identity theft, and so on. And we can also use XSS to essentially escalate to more serious attacks and so on. All right. Cross-site scripting can also be used in conjunction with other types of attacks. For example, cross-site request forgery. All right. We'll talk cross-site request forgery, CSRF, or CSRF or XSRF, is an attack where the attacker tricks the victim into performing actions on their behalf. So the impact of the attack depends on the level of permissions that the victim has, but we could take advantage of the fact that the website completely trusts a user once it can confirm that the user is indeed who they say they are. All right, so we have this sleeping giant in the world of web application security called cross-site request forgery, and again, something that's not typically taken too seriously, but it is shows up on the OWASP top 10 list as well. All right, so there are several different types of cross-site scripting attacks. We have stored persistent XSS, we have reflected non-persistent XSS, DOM-based XSS, and so on. Again, it's a little bit beyond the scope of this class to get into the specifics, and we could spend quite a bit of time talking about these particular threat vectors and attack vectors, but our goal here is to kind of introduce these general concepts. Now, there are two cross-system, two kind of, I guess, directions or let me say stages, right, to a typical XSS attack. Number one, we run malicious JavaScript code on the victim's browser. So we first have to find a way to inject that malicious code or that payload into the web page that the victim goes to. Then number two, the victim has to visit that web page with that malicious code. If the attack is directed at a particular victim, the attacker can use things like social engineering or phishing to send malicious URLs to the victim and so on. All right? Now, in order for step one to be possible, the vulnerable website needs to directly include user input in its pages. An attacker can take that input and insert a malicious string that will be used within the web page, and it's going to be treated as source code by the victim's browser. There are different variations or variants of the XSS attack where the attacker basically lures the user to visit a URL by using social engineering techniques, but the payload is part of that link that the user clicks. All right. So we see here a snippet of information. If the web application does not validate input data, the attacker can steal a cookie, for example, from an authenticated user. This malicious code it's a post that starts with script type equals text/JavaScript. That's going to tell your browser that the lines following are the JavaScript code that we need to run, and we're not sending something that needs to actually be created or populated on the web page itself. This is a cookie grabber script. It passes the content of the cookie to a PHP script in the victim cookies variable, and then anybody that opens up this particular web page will be vulnerable to this, right? The attacker can then impersonate that victim by using that cookie. And we did talk about, I briefly mentioned that, stealing cookies is one of the options for XSS. The other is, being able to spread malware or deface a website and so on. All right. Now we'll talk about stored versus reflective, but I want to talk about a couple of other things before we get into that, right? Let's say, for example, I have a snippet of code that maybe goes and shows the most recent comments on a page, right? So it's some sort of print code, print the most recent comments, and then go into the database and pull out the latest comments. All right, so we take the latest comments from a database, we include that in our HTML page, but it assumes that the comment printed consists only of text and it doesn't contain any HTML tags or other malicious code, right? It is vulnerable to XSS because the attacker could submit a comment that actually contains malicious payload. So, a script, for example, where we say, okay, go ahead and do this. The web server provides that HTML code to the users that visit the web page. When I go in, I look at the most recent comments. The page is going to load in the victim's browser, and the attacker's malicious script is going to execute. All right. The victim doesn't even really know that that's actually happening. All right. Now, going back to our cookie example here, right? We use XSS to steal cookies. This basically allows you to impersonate a particular victim. So I can send the cookie to our own server in a lot of different ways. One of them is to execute a client-side script in the victim's browser, like windows.location, evil.com/cookie, document cookie type of script. That's basically what we're, not the same thing that we're looking at here, but very similar to what we look at here. All right. So the attacker injects the payload into the website's database. We do that by submitting a vulnerable form with that malicious JavaScript content, The victim requests that web page from the web server. The web server serves the victim's browser the page with that attacker's payload as part of the HTML body that's being presented by that page. That victim's browser then executes that malicious script contained within the body itself, and in this case, it sends the victim's cookie to the attacker's server. That attacker now simply needs to take that, extract that victim's cookie, and then utilize that victim's cookie for impersonation. All right. Now, like I said, there are many, many different things that we could talk about here. We could get into so much more detail about each of these individual types of threats, right, and threat vectors. For example, when it comes to cross-site scripting attack vectors, there are some very, very common XSS attack vectors that we can use to compromise the security of a website or a web application through XSS. We can use a script tag. Script tags are probably the most straightforward XSS payload. A script tag can reference an external JavaScript code, or you can embed the code within the script tag itself to run a particular script. That's what we're kind of seeing in this particular example. We also have JavaScript elements, JavaScript event attributes, like things like onload or onError can be used with different tags. This is a very, very popular XSS attack vector as well. Onload, alert, or onload, XSS or whatever. We can also use body tags. We can deliver scripts within the body by using event attributes or other obscure attributes like the background attribute and so on. We can use image tags. We can actually implement or execute JavaScript in the image attributes itself. We can use iframe tags, so we can embed other HTML pages in the current page. That iframe then could contain JavaScript, but JavaScript in the iframe doesn't have access to the DOM of the parent page because of CSP, right? That's the CSP of the browser, the content security policy. But iframes can still be effective for pulling off things like phishing attacks. We can use the input tag, we can use link tags, table tags, div tags, all kinds of things, right? Now, how do we prevent XSS? We have to sanitize our input. This is a common thing that we've seen throughout all of this discussion, right? Input validation, data sanitization is the way that we protect ourselves. Your application code should never output data received as an input directly into the browser without first checking for malicious code. All right, that's one of the options here. All right, they also mention here using Cisco Umbrella to block the users from accessing malicious websites, using a web proxy. We talked about those two options earlier, meaning that we would have to understand the reputation of those sites in order to be able to proactively block them. We can also do application payload inspection using IPS, and then of course execute. I keep saying that. I don't know why. Maybe I want to do that. I'm not sure. Some users I feel like that, I think. Educate. Don't execute your users. Maybe if they're the ones doing the attack, but educate your users, right? Say, okay, if you see something strange happening in your browser, don't just simply go along with it. Maybe it's an attack and you need to be aware of that. All right. Now, they did talk about different types of XSS attacks, stored or persistent. These are dangerous because they're permanently stored on the server, and reflected or non-persistent would be, we find a website that allows injection, but we only need that for the time that we're actually perpetrating the attack. So just a couple of differences there. Now, the other thing they talk about here is the cross-site request forgery, or the CSRF. I kind of already talked about this a little bit, right? There's two main parts to basically executing a cross-site request forgery attack, right? The first one is to trick the victim into clicking a link or loading a particular page. And this can be done through social engineering techniques, or even just phishing techniques, or basically malicious links that are sent to the user somehow, right? The second part is sending that crafted, legitimate-looking request from the victim's browser to the website. That request is sent with values that are chosen by the attacker, including maybe cookies that the victim has associated with that website. That way, the website thinks that the victim can perform certain actions on that particular website. Any request sent within these HTTP credentials or cookies are going to be now considered legitimate, even though the victim would be sending the request on the attacker's behalf, right? The victim is not actually intentionally sending this information. If a request is made to a website, the victim's browser checks if it has any cookies that are associated with the origin of that website and that need to be sent with that HTTP request. If so, if this is required, these cookies are included in all the requests that are actually sent to that website. The cookie value typically contains authentication data, and those cookies represent that user's session. So this is done to provide the user with a seamless experience, so they're not required all the time to authenticate, to gain access to every single page they want to visit. All right. Now, if a website actually approves the session cookie and then considers the user session valid, an attacker can use this CSRF, or this forgery, to send requests as if the victim was sending them. All right? You can see how that could be pretty beneficial in this particular case. The website's actually unable to distinguish between the requests that are being sent by the attacker and those that are actually being sent by the victim, since they're always being sent from the victim's browser with their own cookie, with their own credentials. All right, so we're just basically taking advantage of the fact that the browser sends the cookie to the website automatically with each request. All right, now this will only work if the victim is authenticated. That means that the victim has to be logged in for the attack to be successful. Because the CSRF attack is used to bypass the authentication process, there could be some elements that are not affected by these attacks, even though they're not necessarily protected against them. Publicly accessible content, for example, would probably not be a big concern, right? A contact form in a website, typically safe from a CSRF attack. All right? We don't have to have any privileges to submit a form. All right? Now, we do see an example here. The CSRF malicious link that's shown below could cause the web server to accept the input from the user and process it as if the user intended to submit a password change. All right, new password. Here's another example. We assume that the Human Resources Department of Company X is leveraging a web portal that updates the salary information of the company's employees. Wow, that would be kind of cool, right? To execute that process, the Human Resources Department needs to complete the following. Number one, they have to authenticate to the web application, proceed to raise the salary area of the portal, and complete the form with the name of the employee and the amount of the raise. Once the preceding steps are completed, the user is required to press the submit button and process the form to complete the change. Assuming that the submitted form was for an employee who's named John Doe and who's given a raise of $1,000, the post will get generated. User John Doe and amount equals 1,000. Now, depending on the application, the browser may actually validate that authentication session using that stolen cookie. All right? If I send a request to a specific domain, this is what I was talking about previously, we need to send the cookie that's associated to that domain in the web server, and that may already be stolen and subsequently forged. Now, they do mention here countermeasures include educating our users, right? Again, this is something that's really difficult in this case because we're not looking for a specific event, right? In fact, your regular user is probably not even going to be aware if their cookie is stolen or if this is happening. You know, certainly you want to instruct users not to click on links that they don't recognize or links they receive in an email and so on. But with CSRF, there are some other techniques that are being proposed. Using a refer header, using an HTTP only flag, sending an X request with custom header, using jQuery, and so on. But the problem is these tools might work in certain scenarios. They don't necessarily work in all scenarios. So it is important, obviously, to have the ability to educate your users and whatnot. And you have to look at specifically what's happening in your environment to identify what might specifically apply to mitigating this potential type of attack in your environment. The most popular method to prevent cross-site request forgery is to use some sort of challenge token that gets associated with a particular user and that gets sent as a hidden value in every site-changing form in the web application. This is called an anti-CSRF token or CSRF token. I'm not going to get into the details of that. Certainly you can go and research that if you want to find out more about that, but that is one of the more popular mechanisms today. All right, our question here, which three statements apply to XSS? Malicious scripts are injected into web pages and executed on the client side. That is absolutely true. This is a client-facing issue. A web application processes an attacker's request using the victim's authenticated session. That is not true, right? The web server doesn't process the attacker's request using the victim's authenticated session. It uses the cookies. Malicious scripts are injected into web pages and executed on the server side. That's not true. It's done on the client side. Scripting languages used by XSS have security weaknesses. Absolutely. That's what we talked about, right? We need to make sure that we kind of avoid that. Clicking an infected link causes a malicious script to run in the background process. It could. Absolutely. Scripting languages used by XSS do not have security weaknesses. That's not true. That's the opposite. All right. All right, we got one more section, then we'll wrap up with our summary challenge. We'll see you there in a little bit. So the final thing we're going to talk about in this module is email-based attacks. There are different types of attack vectors that get used by hackers to target email systems. And it is important to note as we go through this section that while different attack vectors could employ different methods, they ultimately have a specific purpose when they're executing that particular attack. The most common technique used to attack emails includes things like identity theft, phishing attacks, virus and spam emails. So what we're going to do in this brief last section here is just take a closer look at some of the common techniques that threaten email security. Now you can see here that they do go through some description about some of the statistics that have been gathered about different types of email attacks, and we do see some examples of email threats. For example, attachment-based email threats. That's pretty obvious to kind of understand. You know, somebody sends embedded content inside of an email that gets automatically executed or gets clicked on by the email user because they believe that that email is coming from a trusted source, or they believe that email is a trusted file, right? For example, one of my employees received an email in our finance department that said it was a document from the IRS, and the spoofed email address looked like it came from irs.gov, and it looked like it was an attachment, and there was a sense of urgency placed on the document because they said in the body of the message, your tax filing, and this happened to be right around tax season, of course, your tax filing has been rejected. You need to open the form and correct the issues. So it can be really, really difficult to stop those types of threats from spreading because of the way that these messages are crafted and they're delivered to the client. Identity theft, of course, is one of the common goals of an email threat. Many organizations these days are using things like Office 365 or G Suite or Zoho or similar services to manage their email systems. But other than hosting emails, Services like these offer a suite of business tools to manage information all in kind of one location. And some apps in that suite include added things like cloud storage space, project management applications, collaboration tools, office suites, and so on. Because these are all part of the same suite as that email service, end users don't really need to separate their different login credentials to access them, regardless of whether the company uses any of these particular services or even their own proprietary service. We tend to face the same set of consequences when a hacker or an attacker manages to get a hold of the user's identity, i.e. their login credentials. And employees usually use the suite to store their confidential data, and in a short period of time, that could be exposed if an attacker gains a handle on the employee's email account, and email identity theft, even though it may not seem like a lot, maybe we can exfiltrate some information from the email system, could actually result in much larger types of damages. Another mention of an example of an email threat vector is email spoofing, right? Email spoofing is a technique used in a lot of different spam and phishing attacks to trick users into thinking that a message, and this is kind of what I was just describing a minute ago, comes from a person or an entity that they know or trust. A lot of the botnet traffic we saw in the 90s and in the early 2000s these botnets were created by sending attachments to an email that appeared to come from people in your contact list, or it actually was addressed from people in your contact list because your contact list was compromised. In a spoofing attack, basically what happens is the sender forges the email headers so that the client software displays that fake or fraudulent sender address, which most kind of, I wouldn't say uneducated, but non-technical users might take at face value. Unless they actually go in and inspect the header more closely, we see that forged sender in the message, and if that name is recognized, they're most likely going to trust it. So they'll click on the malicious links, they'll open the malware attachments, or they'll send sensitive data and even perform what normally would be secret transactions, or financial transactions, or exfiltrate information, even though their intent is certainly not to do that. Email spoofing is possible basically because of how email systems are designed. Outgoing messages get assigned a sender address by that client application. The outgoing email servers have no way to tell whether the sender address is legitimate or spoofed, not some of the traditional email systems anyway. Recipient servers and even anti-malware software could help to detect and filter those messages, but not every email service has those types of services in place. You could still review the email headers that are packaged with the message to identify whether or not the sender's address is forged, but that could be a difficult thing as well. And of course, the goal of email spoofing is basically just to trick the user into believing that that email is from someone that they know or trust. It could be a colleague, it could be a vendor, it could be a subject matter expert, it could be a brand like Cisco, and by exploiting that trust, the attacker asks the recipient to perform a task. It could be to divulge information or to take some other action that they normally wouldn't take. We saw a lot of these going around with a PayPal phishing attack, where not only was the address the address looked as though it was coming from PayPal, the message body was formatted in a way that it actually looked like a PayPal message, and you would say, oh, this is a PayPal receipt for something that costs a lot of money and looks like it came from my account. Your first inclination is, oh my gosh, what did I buy, or what did somebody buy on my account? And rather than check the email, you're going to go ahead and click the link, which may even direct you to a fake website that looks like PayPal, and then you'll unknowingly provide your credentials. All right, so that's a type of social engineering, of course, and we're trying to trick the user into successfully entering their credentials to authenticate the account when they're actually not really authenticating at all. With a typical email client like Microsoft Outlook, the sender address is automatically entered when the user sends a new email message. But an attacker can programmatically send messages using basic scripts in languages that configures the sender address to an email address that they choose. Email API endpoints then allow the sender to specify the sender address regardless of whether that address actually exists. And outgoing email servers can't really determine whether the sender address is legitimate or not. So that outgoing email is retrieved, it gets routed using SMTP. When a user clicks send in their email client, the message gets sent to the outgoing SMTP server that is configured in that client software. The server identifies the recipient domain, and then it routes the email to that domain email server, and then the recipient email server routes the message to the user's inbox. All right, now for every hop that a message takes as it travels across the internet from server to server, the IP address of each server is logged and included in those email headers. And these headers divulge the true route and the sender. The only thing is most users don't really know what they're looking at, right? Even if they were to look at those headers, they really wouldn't know what they're looking at. The three major components of an email, by the way, are the sender address, the recipient address, and the body of the message. Another component, and I'm spending a lot of time on this because I think it's really important, but another component often used in phishing is the reply to field. This field is configurable from the sender and can be used to actually facilitate phishing attacks. The reply to address tells the client email software where to send the reply, which can be different from the actual sender's address. So the email server and the SMTP protocol don't go through and validate whether this email is legitimate or whether it's a fake email, a forged email. It's up to the user to realize that the email is possibly going to the wrong recipient. All right, so that's something to consider. Now, SPF, or the Sender Policy Framework, is a set of security protocols. It was developed in 2014, and it actually works in conjunction with DMARC, the Domain-Based Message Authentication Reporting and Conformance Protocol, to stop malware and phishing attacks. SPF can actually detect spoofed emails, and it's really kind of the most common way that email services today try to combat phishing attacks. It is the responsibility of the domain holder, though, to utilize SPF. To utilize SPF, the domain holder has to configure a DNS-TXT entry that specifies all the IP addresses authorized to send email on behalf of their particular domain. With this DNS entry configured, the recipient email servers look up the IP address when receiving a message to ensure that it matches the email domain's authorized IP address. If there is a match, the received SPF field pushes out a pass value or pass status. If there isn't a match, you'll get a fail status, and you should review that status when you're receiving the email, especially if that email has links, attachments, or any kind of instructions. Even with this kind of email security in place, malicious messages still can reach the user's inbox. And it's really up to the user and the employee to make the right decisions on what to do with that email, right? Never click links to access a website when you're asked to authenticate. Always reference the domain name in the browser and make sure it's an accurate domain name. Make sure that that domain that you're accessing is secure. In other words, it has a valid certificate that authenticates the trustworthiness of that domain, or at least verifies the authenticity of that domain. You could take steps, of course, to view the email headers. Look at the email headers in your inbox software. Open email headers and look for that received SPF section for a pass-fail response if you happen to have that open. Of course, that's not really that practical, right, from a standard user's perspective, but it is something that you could do. You could copy and paste the content of an email message into a search engine. If it's common in a phishing attack most likely other people have reported or published that information on the internet. Always be suspicious of email from an official source that has bad spelling or bad grammar. Of course, don't open attachments. Any emails promising that you're going to inherit millions of dollars from King Mahmoud or whatever from some African country probably is not going to be accurate or not going to be legitimate. All right. Also, beware of emails that tend to create a sense of urgency or danger. Phishing attacks often play on social engineering concepts. The human propensity to be nervous or concerned about transactions on their computer and whatnot. Anything that warns of pending account closures or payment failures or suspicious activity on your account. Of course, you want to be aware of that, right? So the next one in the list is spam. Of course, I don't really have to talk too much about spam. Spam is just spam, right? Sometimes it's malicious, sometimes it's just annoying, but it's a bunch of email that you don't really want to receive. Usually containing advertisements. Maybe some spam has some nefarious purpose or whatever in the sense that they want to get you to do something or react. But generally, spam is just annoying, right? Just you get so much of it, you miss the valid emails or you miss the important emails. And the clients themselves have gotten a lot better at being able to identify the spam, but these botnets that get created make it extremely difficult because the messages are coming from lots and lots of sources and so on. All right. But there's lots of ways to combat that, but it's kind of an uphill battle for most people. An open relay is basically a simple transfer mail protocol server that is improperly configured to allow unauthenticated relay of email messages. And spammers can connect to those servers and then use them to send email and provide them the ability to still forge sender information for those messages. Some block lists actively target open relays to block those abusive practices of spammers who actually use those unsecure servers. But it is a big problem. There are services that are available to you online to check whether you have an open relay or if your server's configured as an open relay. MX Toolbox is one that we use. Checkr.com. That's CHECKOR.com. But basically, you want to ask make sure you go into your SMTP server and on the mail relay parameters say that you're only going to send mail from known domains or IP addresses, and just make sure that you have the appropriate security in place. This is less and less of a problem than it used to be, but it is definitely a spammer's dream. If they can identify one of those open relay servers, you can be assured that those servers are going to be used at some point for spamming. All right. Another very interesting way to play on the human condition is to use a homograph, or what they call homoglyphs. A homoglyph is an attack or a homograph, is an attack that uses these homoglyphs, characters that use other character sets like Greek or Cyrillic that have letters that look almost the same as the Roman equivalents. Cyber criminals can register domain names that look on the surface to be identical to an existing domain name, and then that can be used to capture things like passwords or other sensitive information from the user. A good example would be if somebody registered google.com, but instead of using the Unicode character 043E or a Cyrillic small letter O, they could use the other characters that could be used to represent that O. Here's an example here where they use, rather than the standard letter of A, they used a homoglyph of the letter A in Unicode format. So if you look at the PayPal.com, you'll notice in the first instance of PayPal.com, let me go ahead and highlight that there. You look at this, oops, sorry about that. you look at this and it looks on its face legitimate, right? If you're reading it quickly, if it's kind of mixed in there with a bunch of other information, you may not notice that the first A and the second A are different from each other. You might glance over that, and in that case, you're going to be stuck with accessing a fraudulent site based on the use of that homoglyph in that process. All right, so definitely something to take a look at and make sure that you monitor for. All right, if you look at the URL via DNS, so here's the PayPal.com. We do a dig on it. We can see that it resolves differently, right? Dig PayPal.com. The first dig, we can see that the domain is p/201/145ypal.com, whereas if you dig the legitimate PayPal.com, that resolves to, of course, PayPal.com. All right, now in the original implementation of domain names, they were designed to support only ASCII characters. But the IDN, or the Internationalized Domain Name Specification, was released in 2003 that allows just about every Unicode character to be used in the domain names. Now, granted, people aren't going to do that normally, right? Because how are you typing those domain names in when you're trying to access them? It's certainly not something that you're going to be able to do with a standard keyboard. So we don't necessarily see these Unicode characters used by legitimate domain names. But these attackers are sophisticated. They know how to trick people. That's their goal, is to trick you into believing that something is legitimate. All right. So other countermeasures, of course, could include deploying email security appliances like ESA to look at different email threats. We'll talk a lot about ESA later on as we move through the rest of our sections here. We have a whole module on ESA, actually. And then educate your users. Make sure that the users are aware of what types of threats exist and how to look for those things, and how to, especially when it comes to email. It's a really, really important concept, because a lot of these things can be mitigated. A lot of the potential damage can be mitigated by utilizing just common sense and common knowledge, and that's an important aspect. All right. So, which three threats are email based? Spam, absolutely. SQL injection, of course not. Come on, there we go. Attachment based attacks, absolutely. Email address spoofing, we talked about that. Cross-site request forgery, cross-site scripting, and insufficient user authentication, not the case. All right. All right, let's go ahead and wrap up our lesson here by going through our summary challenge, and we will get into the next module. So the first question in our summary challenge, which two options determine the speed at which a password can be cracked using the brute force method? This would happen to do, this is what we call the Password Haystack. And if you actually go out to Google and you search on Password Haystack, you can see several different calculators that will, based on the IOPS and the computing power and whatnot, the complexity of the password and the entropy of the password, how long would it take to actually crack that password? Is it offline? Is it online? Are we using brute force? Are we using a dictionary attack? Are we using rainbow tables if there's a hash involved? Those kinds of things. The willingness of the victim to share personal information may or may not come into play, right? If you don't have a strong password policy, it's possible that somebody could be choosing their birthday or a combination of their first name and last name and so on for their password. But the reality is, in most cases, we at least have some sort of level of randomness that we require for passwords, or at least some sort of passphrase. So I wouldn't say that that's necessarily one of the methods. Plus, that isn't brute force anyway. That is considered social engineering. All right. So the attacker's speed, computer speed would apply. The attacker's list of the commonly used passwords, that could be the dictionary And if that list is comprehensive, yeah, maybe. But the thing is what is the size of the password, right? What is the key space? We call that key space. It allows us to identify the length of the password. And of course, the larger the key space, the more iterations of a particular password you can have, and the more iterations you have to go through when you're trying to brute force a password. So the length, the complexity, and the computer that's doing the array that's trying to crack the password would play into that. Which statement describes how a DNS amplification and reflection attack is implemented? By predicting the next transaction ID that's used in a DNS query and using that to construct a spoofed DNS message. That is not the case. Amplification and reflection uses open DNS resolvers. And again, this is an attack where we have to have open DNS resolvers to do that. By falsifying and spoofing RR information in the DNS resolver, negative. By depleting DNS resolver CPU, memory, and or socket buffers, no. By using multiple DNS open resolvers to send DNS response messages to the target device. Absolutely. Absolutely, that's correct. Which two countermeasures should an administrator employ to protect against DNS tunneling? Monitor the DNS for suspicious activity. Of course, that's always going to be a general countermeasure for any security scenario. You always want to look for suspicious activity, so I would say that would apply to just about any scenario. Deny all DNS transactions. You couldn't do that. That wouldn't be possible. It'd be very difficult to, to facilitate communication on the internet if you're denying all DNS transactions. Encrypt the DNS communication using a hash. Well, there's a couple things wrong with that. Encrypting DNS communication, potentially could be something to provide for some confidentiality, but DNS tunneling still, just because we're encrypting the data doesn't mean data still can't be inserted into the DNS fields in the DNS payload. Plus, we also don't encrypt using a hash. We encrypt using encryption mechanisms like AES or PKI encryption methods like public and private cryptography. Hashing is used for message integrity, not for confidentiality. But it still wouldn't matter anyway, because just because we're encrypting the data doesn't mean that we're somehow verifying what's carried in the payload, and if that information in the payload is actually accurate. Deploy a solution like Cisco Umbrella. We talked about that specifically. We will spend a whole module talking about Cisco Umbrella to be able to block that DNS tunneling traffic. Block all DNS traffic on the firewall. Again, that's not something that's really going to be possible. Okay? So match the action to the stage of the web attack. So I guess we have to kind of put these in order here. Let's see. I'm going to kind of scan through them. And let's see, the victim visits a compromised site. That would probably be number 1. Whoa, that's too big. Hold on one second. Get rid of that. So this would definitely be number 1, right? We visit the site that has the malicious code. The exploit kit is delivered by drive-by download. That would definitely be number 2. The exploit kit sends a request to the exploit kit server to get the exploit code that compromises the vulnerable software on the machine. Well, it looks like these are already in order. That's not very creative, Cisco. Yeah, that's number 4 and that's number 5. That's how it happens. That's the order it happens in. The malicious code connects the victim's machine to the malware downloaded download server to retrieve that payload, and then the encrypted malware is decrypted and executed on the machine. Might have been nice if they would have mixed those up a little bit. They mixed the numbers up on the right, but they put them in the order on the left. That's kind of strange. All right. Which 2 statements are true about malvertisements? We talked about this. Malvertisements are sometimes set up to affect all visitors to a site only during a specific period of time. We definitely talked about that as opposed to targeting a specific host. Malvertisements, malicious code remain forever. Not necessarily true. And we talked about that specifically as well. Malvertisements affect both trustworthy and untrustworthy sites. Absolutely. We can compromise a legitimate site to deliver malvertisements. Infections only occur when the victim clicks the malvertisement. Not necessarily true. Certainly more damage could occur if they click that advertisement or that malvertisement, but that doesn't necessarily have to happen. What is the primary goal of an attacker when using an iframe or HTTP 302 cushioning? To help the user find the correct web page location. Well, that's the purpose of HTTP 302. That is not the purpose necessarily of an iframe or HTTP 302 cushioning. To ensure that the victim's web browser ends up on the attacker's web page, which serves out that malicious exploit. Absolutely. That's by definition what HTTP 302 cushioning is. All right, that means the other two are not correct. Which two options are examples of command injection attacks? Well, certainly SQL injection and cross-site scripting. DNS, TCP injection, we're not executing commands in this case. We're dealing with malformed payloads and whatnot, but not actually injecting commands that would execute in the operating system. Which two outcomes can be caused by a successful SQL injection attack? Well, you could definitely get information from the database. There's no doubt about that. Extracting all the database accounts and password hashes from the database, probably not going to happen with a SQL injection attack. You could definitely inject, get some information or exfiltrate some information, but you're not going to get all the information. Inject malware in the database server. No, we're not affecting the operating system of the server. We're not affecting the applications on the server. We're basically exfiltrating information from the server itself. Execute administration operations on the database. Yep, absolutely. On the database itself, not the server, but on the database itself. All right, because we're affecting the database. Last two questions. Which two countermeasures reduce the threat of CSRF? Deploy an email security appliance. Negative. This doesn't have anything to do with email. Cross-site request forgery is or cross-site scripting, I should say, and request forgery is a database threat, not an email threat. Educate the users to look for phishing attacks. Absolutely. We're talking about forgery, right? We're talking about somebody stealing your authentication credentials, which typically is done with phishing. Deny access to the public internet for your workstations and laptops. I mean, I suppose that is a mitigation technique, right? That is what we call avoidance. If you're afraid that your parachute's not going to open, don't jump out of a plane. If you're afraid of some sort of attack on the internet, don't go to the internet. But actually, attacks can come from the inside as easily as they can come from the outside, sometimes even more easily. Developers need to follow their security best practices. Yes, we talked about what all those best practices were when you're dealing with databases. All right, match the type of attack to its example. The last one here, kind of a mix and match. You've won $1 million. Please see the attached file. That would definitely be an attachment. PayPal.com. And that's interesting. They 401k services at your company. That would definitely be spoofing. I think the intent with the PayPal.com was the homoglyph, even though they didn't use it. We should have seen that other A there, and then spam. Hey, you won $1 million. All you need to do is pay the taxes, and you can collect it. Yeah. All right. Okay. So that wraps up this module. We're going to go ahead and finish up this module. Our next module, describing common endpoint attacks, we're going to take a look at some of these different types of attacks in more detail and some additional attacks. And then we're going to start to get into our overall network security technologies.